The first humans to reach Mars will be heroes. They will also be, from the moment of launch, dying in ways medicine can slow but cannot stop. The radiation is invisible, the bone loss is silent, the psychological unraveling is gradual, and the planet waiting at the end of the journey has been trying to kill things for 4 billion years. What kind of person boards that rocket anyway? If this kind of content moves something in you, make sure to give this video a like. Now let's get started. Mars is not next door. On average, it sits about 225 million kilometers away from Earth. But that number shifts dramatically depending on where both planets are in their orbits around the Sun. At their closest, a moment astronomers call opposition, Mars can be as near as 54.6 million kilometers. At their farthest, it stretches out to over 400 million kilometers. And because of this orbital dance, mission planners can only launch toward Mars during specific windows that open roughly every 26 months. Miss the window and you wait more than 2 years for the next one. The trip itself, using our current best propulsion technology, takes somewhere between 6 and 9 months. That is not a weekend road trip. That is not even a long ocean crossing. That is 6 to 9 months inside a metal capsule, floating through a vacuum, with no rescue possible, no quick return, and no way to just pull over if something goes wrong. Every astronaut who has ever been in trouble in space, think of the Apollo 13 crew, think of situations aboard the International Space Station. They had one thing those Mars astronauts will not have: the ability to come home quickly. Earth was close enough that communication delays were measured in fractions of a second. Help was conceptually reachable. On a Mars transit, a radio signal from Earth takes anywhere from 3 to 22 minutes to arrive, depending on where the planets are. And that means if something goes catastrophically wrong, you are on your own. Mission control cannot save you in real time. The crew has to save themselves. This is not speculation. NASA has been studying this problem for decades. Their human research program has identified what they call the 5 hazards of human spaceflight for deep space missions. And when you hear them laid out one by one, the weight of what the first Mars crew will face starts to become very, very real. The first hazard is space radiation, and this one deserves its own chapter, because it is arguably the most insidious danger of the entire mission. On Earth, we are protected by 2 invisible shields. The first is our planet's magnetic field, a vast, dynamic bubble generated by the churning liquid iron in Earth's core. It deflects the solar wind, those streams of charged particles constantly blowing off the sun. The second shield is our atmosphere, a blanket of gas roughly 100 kilometers thick that absorbs and scatters the radiation that does get through. In deep space, you have neither of these. The moment a spacecraft leaves low Earth orbit and heads toward Mars, the crew is exposed to 2 types of radiation that are fundamentally different from anything most people ever encounter. The first is solar energetic particles, intense bursts of radiation that erupt from the sun during solar flares and coronal mass ejections. These events are somewhat predictable, and spacecraft can be designed with shielded storm shelters where crew members can retreat during the worst flares. But the second type is far more troubling. Galactic cosmic rays, high-energy particles that come not from our sun, but from exploded stars, from supernovae, from the violent deaths of suns across the galaxy, stream through the solar system constantly, from every direction at nearly the speed of light, and they are extraordinarily difficult to shield against. The heavier the shielding material you add to a spacecraft, the more secondary radiation it can actually generate when those particles slam into it. It is a deeply frustrating engineering problem that physicists and aerospace engineers are still working to solve. NASA's data from the Curiosity rover's radiation assessment detector, which measured radiation during its own transit to Mars between 2011 and 2012, gave us our first real measurement of what a human crew would face on that journey. The results were sobering. Over the roughly 253 days of transit, the instrument recorded a radiation dose equivalent to roughly 300 millisieverts. To put that in context, the current career radiation limit for NASA astronauts is 600 millisieverts. That means a single round trip to Mars, just the travel, not even counting time spent on the surface, could use up half of an astronaut's entire career radiation allowance. For countries like Russia, some limits are slightly higher, but no international standard makes this number comfortable. And radiation does not just cause cancer, though the elevated lifetime cancer risk is real and significant. High-energy galactic cosmic rays can penetrate the skull and interact with brain tissue. Studies on rodents exposed to simulated cosmic ray environments have shown measurable cognitive effects, reduced performance on memory tasks, increased anxiety-like behavior, signs of neurological damage. A 2016 study published in Scientific Reports, led by researchers at the University of California, Irvine, found that mice exposed to charged particle radiation similar to what astronauts would encounter in deep space showed significant impairment in learning and memory, along with structural changes in the brain's neurons. We do not yet fully understand what 6 to 9 months of this exposure does to a human brain, and the first Mars crew will find out. And I actually made a whole separate video breaking down exactly why Mars would be a horrible place to live. It's on the card above. We are talking about the surface conditions, the atmosphere, the psychological toll, all of it in detail. It honestly pairs perfectly with what we are covering today. The link is in the description and pinned on the comments, but back to the transit. Because radiation is only the beginning, the second major hazard the first Mars crew will face on that long journey is isolation and confinement. Human beings evolved in social groups. Our nervous systems are wired for connection, for the comfort of familiar faces, for the grounding presence of nature, sunsets, wind, the smell of rain on dry earth. Strip all of that away, lock 6 people in a module roughly the size of a small apartment, and send them hurtling through a void where the nearest other human being is getting farther away every single second, and you create a psychological pressure cooker that we still do not fully understand how to manage. Space agencies have been studying this through analog missions, simulated Mars missions conducted in isolated environments here on Earth. The Mars 500 experiment, conducted between 2010 and 2011 by Russia's Institute of Biomedical Problems in collaboration with ESA and other partners, locked 6 volunteers in a facility in Moscow for 520 days, simulating the duration of a Mars mission including surface time. What they found was illuminating and, in places, deeply concerning. Sleep disorders became widespread, activity levels dropped, some crew members showed signs of sedentary behavior that mirrored depression. The monotony, the confinement, the artificial light, all of it ground people down in ways that are difficult to quantify but impossible to ignore. On a real Mars mission, the psychological pressure would be compounded by something the Moscow simulation could never truly replicate: the knowledge that there is no way out. Every crew member on that spacecraft will know every single day that if they need to leave, if the walls start closing in, if a relationship in the crew fractures beyond repair, if someone has a breakdown, there is no door they can walk through. There is no emergency return flight. The hatch opens to vacuum. You push through or you do not make it. We have only just scratched the surface of what awaits the first humans on this journey. And what is coming in the next part of this video is in many ways even harder to stomach, because we have not yet talked about what 6 to 9 months of weightlessness actually does to a human body. And the answer involves your bones dissolving, your muscles wasting away, your vision changing permanently, and your heart literally shrinking. This is not metaphor, this is physiology, and it is one of the most profound challenges standing between humanity and Mars. Stay with me, because part 2 is where things get genuinely shocking. Your body is a masterpiece of adaptation. Every system inside you, your muscles, your bones, your cardiovascular system, your immune response, your vision, every single one of them evolved under one assumption, one constant that has been true for every single human being who has ever lived, for every single ancestor stretching back millions of years through the fossil record. That assumption is gravity, specifically one full unit of Earth's gravity, pulling down on you at 9.8 meters per second squared every second of every day of your entire life. Roam that, and the body does not simply float peacefully through space like the astronaut footage you have seen. It begins to fall apart, quietly, methodically, in ways that compound on each other over weeks and months, until the person who boarded that spacecraft and the person who arrives at Mars are, in measurable biological terms, not quite the same. Let us walk through what actually happens. The moment weightlessness begins, the moment that spacecraft cuts its engines and enters free fall toward Mars, your body receives a signal it has never received before in the history of human evolution. There is no up, there is no down, and the fluid in your body, which on Earth is constantly being pulled toward your legs and lower torso, begins to redistribute. It shifts upward toward your head and chest. Astronauts describe this sensation in the early days as feeling permanently congested, like having a bad head cold that never goes away. Their faces puff slightly. The veins in their necks become more visible, and this fluid shift sends a confusing message to the kidneys and the cardiovascular system, a message that says there is too much fluid in the body, which triggers the body to start shedding it. Astronauts urinate more in the first few days. They lose plasma volume, and this sets off a cascade of changes that ripples through nearly every organ system. The heart, which normally works hard against gravity to pump blood upward to the brain, suddenly finds its job dramatically easier. And what happens to a muscle when it no longer has to work as hard? It shrinks. Studies using echocardiograms, ultrasound imaging of the heart, on astronauts returning from long-duration missions on the International Space Station have documented measurable reductions in heart mass. The heart becomes more spherical in shape, less elongated, and while the body compensates to some degree, the implications for a mission lasting 6 to 9 months of transit, followed by an extended surface stay, are serious. A weaker, reshaped heart returning to a gravity environment, even Mars's gravity, which is roughly 38% of Earth's, has to work harder to readjust. And during that readjustment period, the risk of cardiovascular events is elevated, but the heart is almost a footnote compared to what happens to the bones. Bone is not a static material. It is living tissue, constantly being broken down and rebuilt in a process called remodeling. On Earth, the mechanical stress of gravity, the weight of your own body pressing down through your skeleton with every step you take, is one of the key signals that tells your body to keep building bone. Remove that signal and the balance tips. Bone resorption, the breaking down of old bone, continues, but the formation of new bone slows. The net result is bone loss at a rate that, in the early days of long-duration spaceflight, was genuinely alarming. Studies from the International Space Station era showed astronauts losing roughly 1 to 2% of bone density per month in weight-bearing areas like the lower spine and hips. That is 10 to 20 times faster than the bone loss seen in post-menopausal women experiencing osteoporosis, which is itself considered a serious medical condition. Modern exercise protocols. Astronauts on the station are required to exercise roughly 2 hours every day using resistance equipment specifically designed to simulate weight-bearing loads, have dramatically improved this picture. Current long-duration crew members lose significantly less bone than their predecessors did, but they still lose some. And the exercise equipment that fits on the International Space Station may not have a perfect equivalent on the compact spacecraft heading to Mars. Every kilogram of mass is a cost. Every cubic meter of space is precious. The engineering trade-offs are brutal, and then there are the muscles. Without the constant low-level effort of simply standing up, walking, fighting gravity with every movement, the muscles begin to atrophy. The legs, in particular, can lose significant mass and strength over the course of a long mission. Astronaut Scott Kelly, who spent 340 days aboard the International Space Station as part of NASA's twin study, comparing him physiologically to his identical twin brother Mark, who remained on Earth, showed measurable muscle loss despite rigorous exercise. It took months after his return for his body to fully recover, and Scott Kelly came home to Earth's full gravity, to medical teams waiting on the runway, to a rehabilitation program designed specifically for him. The first humans arriving at Mars will have no such luxury. They will step off a spacecraft after 6 to 9 months in weightlessness and immediately be required to function, to operate equipment, to make decisions, to physically manage their habitat. Mars's gravity is lower than Earth's, which helps, but it is not zero, and bodies that have spent months in freefall will feel even that reduced pull as a profound shock to the system. The first hours on the Martian surface may be among the most physically demanding of the entire mission, at the exact moment when the crew is at their physical lowest. Now here is the part that genuinely surprises most people when they first hear it. Vision. Roughly 40 to 60% of astronauts who have spent extended time in space return to Earth with measurable changes to their eyesight. Some experience blurred vision, some show flattening of the back of the eyeball, some show changes to the optic nerve, some develop what looks, on scans, like folds in the tissue at the back of the eye. This condition has been given a formal name, spaceflight-associated neuroocular syndrome, or SANS, and as of today, scientists do not fully understand why it happens or how to prevent it. The leading hypothesis connects it back to that fluid shift we talked about earlier. When fluid redistributes toward the head in weightlessness, it increases the pressure of the cerebrospinal fluid, the clear liquid that surrounds and cushions the brain and spinal cord. This increased pressure is thought to push on the optic nerve and reshape the eyeball over time. But the mechanism is still being actively studied. What is known is that for some astronauts, the vision changes are permanent. They land back on Earth with worse eyesight than when they left, and it does not fully reverse. For a Mars crew whose lives may depend on being able to read instrument panels, navigate terrain, perform surgery, repair equipment in low light, the prospect of progressive vision loss during the mission is not a minor inconvenience. It is a mission-critical threat. NASA's Human Research Program has listed SANS as one of its highest priority research areas. Scientists are investigating everything from lower body negative pressure devices, essentially a suit worn around the lower body that uses gentle suction to draw fluid back downward, counteracting the headward shift, to dietary and pharmaceutical interventions. But as of the time of this video, there is no proven countermeasure. The first Mars crew will be flying with an elevated risk of vision degradation that we do not yet know how to fully prevent. And there is one more physiological dimension to this that deserves its own moment of attention, because it sits at the intersection of biology and something much deeper, something almost philosophical. The immune system changes in space. Multiple studies have documented that the immune systems of astronauts behave differently in microgravity. Natural killer cell activity, the immune system's ability to identify and destroy abnormal or infected cells, is reduced. Latent viruses, things like the Epstein-Barr virus, and the varicella zoster virus that causes chickenpox, which lie dormant in most adults, have been shown to reactivate in astronauts during spaceflight. A 2019 study published in Frontiers in Microbiology found that astronauts shed these reactivated viruses at rates significantly higher than healthy controls on Earth. Most of the time, this reactivation does not cause illness. The immune system suppresses it before symptoms develop, but the pattern reveals a system under stress. A system that is working harder to maintain equilibrium than it would in a terrestrial environment. On a 6 to 9 month journey to Mars, with a crew living in close quarters, breathing recycled air, under chronic stress, with disrupted sleep patterns and altered gut microbiomes, the immune suppression compounds. The risk of infection spreading through a crew, of a dormant condition suddenly becoming active, of a small medical problem escalating into something serious. All of it is elevated in ways that are deeply difficult to plan for. And here is the thing that makes all of this so remarkable to sit with if you step back from the medical specifics for a moment. Every single one of these threats, the radiation, the bone loss, the cardiovascular changes, the vision degradation, the immune suppression, every single one of them is essentially the universe telling us something. It is telling us that we were made here, that we are Earth creatures, shaped by billions of years of evolution on this specific planet, under this specific gravity, inside this specific magnetic bubble. And every time we try to leave, our bodies register the departure as a kind of emergency. The first humans to go to Mars will be carrying 4 billion years of Earth's biology into a place that has no use for it. And that tension between what we are and where we are going is at the very heart of what makes this mission both terrifying and extraordinary. We have now covered what the journey does to the body, but here is what we have not yet talked about. What happens to the mind over those months of transit? Because the psychological dimension of a Mars mission is not just about boredom or loneliness, it is about something far more primal. It is about what happens to human cognition, human decision-making, and human relationships when you remove every external reference point a person has ever had and replace it with an endless, featureless dark. The research on this is fascinating, deeply unsettling, and almost never discussed in mainstream coverage of Mars missions. That is exactly where we are going now. There is a moment that every astronaut who has spent significant time in space describes in some form or another. It does not happen on the first day or even the first week. It creeps in slowly, somewhere in the middle stretch of a long mission, when the novelty has worn off and the routine has set in, and the walls of the spacecraft feel less like a vessel and more like a container. It is a moment when the mind, deprived of the sensory richness it evolved to process, the changing seasons, the smell of food cooking, the sound of wind, the feel of sunlight on skin, begins to turn inward. And what it finds there is not always comfortable. Psychologists who study long-duration spaceflight call this the third quarter phenomenon. It is a well-documented pattern in isolated and confined environments, not just in space but in Antarctic research stations, in submarine crews, in anyone spending extended time cut off from the outside world. Roughly 3/4 of the way through a mission, morale tends to dip sharply, motivation falters, irritability rises, small conflicts that were manageable earlier suddenly feel enormous. The end of the mission is close enough to be desperately wanted, but still far enough away to feel almost unreal. And in that gap, the mind struggles. Now take that phenomenon and scale it up to a Mars mission. We are talking about a crew of perhaps 4 to 6 people. The exact number varies depending on which mission architecture you look at, but most serious proposals cluster in that range. Spending 6 to 9 months in a pressurized habitat, roughly the size of a modest house, with no ability to step outside, with communication delays that make real-time conversation with Earth impossible, with every resource they consume carefully rationed, and with the full knowledge that they are farther from any other human being than anyone in history has ever been. The record for the farthest a human being has ever traveled from Earth currently belongs to the Apollo 13 crew, who swung around the far side of the Moon in April of 1970 and reached a maximum distance of about 400,000 kilometers from Earth. The Mars transit crew will be 225 million kilometers away on average. At their farthest, depending on orbital positions, they could be over 400 million kilometers from home. Numbers like that are almost impossible to feel emotionally, but the brain tries. And what it produces when it tries is something researchers call Earth out of view phenomenon, a documented psychological shift that occurs when an astronaut can no longer see Earth as a distinct object, when it becomes just another point of light in the sky, indistinguishable from the stars. Astronauts in low Earth orbit, even on the longest missions, can look out the window and see Earth filling their view. It is enormous, brilliant, alive with color and movement. It is grounding in the most literal sense, a visual anchor that tethers the psyche to something familiar, something home. The Mars transit crew will lose that anchor within weeks of departure. Earth will shrink to a blue dot, then a pale dot, then nothing distinguishable at all. And the psychological research suggests this is not a trivial loss. It removes something the human brain relies on at a deep and largely unconscious level for orientation and emotional stability. Jack Stuster, a behavioral scientist who has spent decades studying isolated and confined environments for NASA, has documented through journal analyses of Antarctic expeditions and space missions that the loss of familiar sensory anchors, horizon lines, natural light cycles, weather, the presence of other living things, creates a kind of perceptual monotony that grinds away at mental resilience over time. The brain, which evolved to be constantly stimulated by a changing environment, essentially starts to overprocess internal stimuli when external ones disappear. Thoughts become louder, emotions feel more intense, minor interpersonal frictions get amplified. And here is where the crew dynamics piece becomes genuinely fascinating and genuinely alarming. Research on isolated groups, from Antarctic overwinter teams to submarine crews to the Mars 500 simulation, consistently finds that the greatest psychological risk on long-duration missions is not the individual's mental health in isolation. It is the relationship between crew members, specifically what researchers call crew cohesion. The degree to which a group functions as a united team is extraordinarily fragile under the conditions of extreme isolation, and when it fractures, the consequences can cascade rapidly. A 2017 analysis by NASA's Human Research Program identified interpersonal conflict as one of the top behavioral health risks for long-duration exploration missions. This is not about crew members being unprofessional or poorly selected. These are among the most highly trained, psychologically screened, operationally experienced human beings on Earth. But even they are human, and humans, when confined together for months under chronic stress, with no escape and no privacy, develop tensions that can become operationally dangerous. There have been documented instances of conflict even on shorter missions. During Skylab missions in the 1970s, one crew famously staged what has been described as a mutiny, though that word is contested. Taking an unscheduled day off from their packed work schedule to rest and push back against what they felt was an overwhelming pace set by ground controllers. The astronauts on that mission had been working extraordinarily hard and felt their concerns were not being heard. The incident prompted NASA to fundamentally rethink how it approached crew autonomy and scheduling for long-duration missions. On a Mars mission, the communication delay with Earth changes the crew-ground relationship in a profound way. With a signal delay of 3 to 22 minutes each way, real-time guidance from mission control is simply not possible. The crew will have to operate with a degree of autonomy that no human space mission has ever required before. Decisions that on the International Space Station would involve ground teams, flight directors, and multiple layers of expertise will on a Mars mission have to be made by the crew alone in the moment with the information they have available. And they will have to make those decisions while potentially sleep-deprived, physically compromised by months of weightlessness, under radiation exposure, and in the middle of whatever interpersonal tensions have been simmering for months in close quarters. Yvonne Cayozzo, a researcher who has studied the psychological aspects of long-duration spaceflight, has noted that one of the most dangerous combinations in isolated group environments is high stress combined with reduced communication and perceived lack of control. All three of those conditions will be present on a Mars transit. The crew will be under physical and psychological stress. Their communication with Earth will be limited by physics, and their ability to control their environment, their schedule, their food, their privacy, their escape will be almost non-existent. There is also something that does not get discussed nearly enough in the popular coverage of Mars missions, and that is the emotional weight of what those crew members will be carrying with them. Before departure, each of them will have said goodbye to everyone they love, knowing that the mission will take years and that there is a real possibility they will not return. They will have watched their families, their children, their parents, their closest friends recede into the distance, first physically as the launch site fell away, then electronically as the communication delays stretched the conversation thin. A message sent to a loved one on Earth might take 22 minutes to arrive. The reply takes another 22 minutes to come back. A conversation that would take seconds on a phone call takes nearly an hour. And the emotional texture of that, the longing, the inability to be present for birthdays, for emergencies, for ordinary Tuesday evenings, is a form of grief that is unique to this kind of mission, and that we have no real precedent for managing. Shannon Lucid, who spent 188 days aboard the Russian Mir space station in 1996 and held the American record for longest spaceflight at the time, has spoken about how the psychological weight of extended isolation accumulates not in dramatic moments but in the quiet ones. In the hours between tasks, when the mind wanders home. In the small rituals, a photograph looked at too many times, a piece of music played, until it becomes both comfort and ache. The first Mars crew will have years of those quiet moments. And no one has ever fully mapped what that does to a person. But here is the thing, and this is important, because this video is not just about fear, it is about truth. Every one of these challenges is being studied. Every one of them is being taken seriously by the people responsible for making this mission happen. NASA, ESA, Roscosmos, private organizations like SpaceX, all of them have behavioral health and performance researchers who are working to develop countermeasures, to design better habitats, to select and train crews in ways that maximize resilience. Analog missions in places like the Esheisia's habitat in Hawaii, perched on the slopes of Mauna Loa at roughly 2,500 meters altitude, have tested crew dynamics and habitat designs specifically to understand what works and what breaks down over time. The human beings who go to Mars will not be going unprepared. They will be the most carefully selected, most rigorously trained, most psychologically studied group of explorers in history. But preparation and training can only take you so far into genuinely unknown territory. And Mars is about as unknown as territory gets. There is a phrase that the philosopher and science writer Carl Sagan used, drawn from the physicist Freeman Dyson, that feels incredibly apt here. He talked about the idea that exploration is not the kind of thing you do when you are sure of success. It is the kind of thing you do because the alternative, staying still, staying safe, never knowing, is a kind of slow death of the spirit. The first humans to go to Mars will be carrying that spirit into the void, and the fact that it is terrifying does not make it less magnificent. It makes it more so, but we have been talking about what happens on the way to Mars. We have not yet talked about what happens when they arrive, and the arrival, the entry, descent, and landing is something that engineers describe using a phrase that tells you everything you need to know about how difficult it is. They call it the 7 minutes of terror. Landing on Mars is arguably the single most technically demanding thing human beings have ever attempted to do. The atmosphere is thick enough to create dangerous heat during entry, but thin enough to provide almost no braking force for the final descent. The margin for error is essentially zero, and everything we know about landing on Mars, everything we have learned from every rover and lander we have ever sent there, has been building toward the moment when we try to do it with human beings inside the spacecraft. What happens in those 7 minutes, and what could go wrong, is something that will keep you up at night. If you are enjoying this journey, if it makes you ask questions you never thought to ask before, then subscribing to this channel is genuinely worth your time. You don't want to miss what is coming next. Now let us set the scene. You have survived 6 to 9 months in deep space. Your bones are thinner than when you left. Your heart has changed shape. Your vision may have shifted. Your body is running on recycled air, carefully rationed food, and the kind of psychological resilience that only comes from being pushed to your absolute limit. You and your crewmates have held each other together through the isolation, through the monotony, through the quiet grief of being impossibly far from home. And now finally, after all of that, the planet is right there. You can see it through the window. That pale reddish disk you have been staring at for months has grown into something vast and real and textured. You can see the white smear of the polar ice cap. You can see the dark scar of Valles Marineris stretching across the surface like a wound in the planet's skin. Mars is no longer a destination, it is a place, and in a matter of hours you are going to try to land on it. And here is what nobody fully prepares you for. The landing is not a gentle arrival, it is a controlled catastrophe, a precisely engineered sequence of events that has to work perfectly in the right order, at the right moments, with almost no margin for error. While your spacecraft is traveling at somewhere around 19,000 kilometers per hour, and the entire sequence from atmospheric entry to touchdown takes approximately 7 minutes. 7 minutes in which you are essentially helpless. 7 minutes in which every system has to perform exactly as designed in an environment 225 million kilometers from the nearest repair shop, with a communication delay that means mission control on Earth will not even know you have started entering the atmosphere until the whole thing is already over. By the time the signal telling them you have begun your descent reaches Earth, you will already have landed or crashed. The outcome will already be decided. They will be watching history, not guiding it. This is why engineers at NASA's Jet Propulsion Laboratory coined that phrase, 7 minutes of terror, and they were not being dramatic, they were being precise. Now, to understand why landing on Mars is so extraordinarily difficult, you need to understand something about the Martian atmosphere. Because it is, in the most frustrating possible engineering sense, the worst of both worlds. Earth's atmosphere is dense enough that a spacecraft entering it can use that density as a braking mechanism. The friction generated by slamming into thick air converts kinetic energy into heat, slowing the spacecraft dramatically. That is why spacecraft returning from orbit use heat shields, not because of some quirk of design, but because the atmosphere itself does the hard work of slowing them down. By the time a returning capsule is low enough to deploy parachutes, it has already shed the vast majority of its speed. Parachutes handle the rest. This works beautifully on Earth. It works reasonably well on Venus, which has an atmosphere so thick it is almost oceanic. It even works to a useful degree on Titan, Saturn's moon, which also has a thick atmosphere. Mars has an atmosphere that is roughly 1% the density of Earth's 1%. It is thin enough that it provides almost no meaningful braking force compared to what Earth offers. But, and this is the crucial and deeply inconvenient part, it is not thin enough to ignore. It is thick enough to generate enormous heat during entry, thick enough to require a heat shield, thick enough to be a problem, just not thick enough to be a solution. So the engineering challenge of landing on Mars is essentially this. You have to slow a spacecraft from roughly 19,000 kilometers per hour to zero, using an atmosphere that gives you maybe 30% of the braking help you would get on Earth, and then somehow cover the remaining velocity deficit with hardware that has to fit inside your spacecraft, survive the heat of entry, and function perfectly in an alien environment it has never been tested in at full scale. For robotic missions, rovers and landers that are relatively light, engineers have developed increasingly creative solutions. The Mars Pathfinder mission in 1997 used airbags bouncing to a stop on the surface like an enormous beach ball. The Mars Exploration Rover's Spirit and Opportunity used the same approach. The Phoenix lander in 2008 used retro-rockets, engines that fire downward to slow the final descent. And then there was Curiosity in 2012 and Perseverance in 2021, both of which used the most audacious landing system ever devised. A system that, when the engineers first proposed it, was reportedly met with stunned silence in the room, followed by the kind of laughter that is really just disbelief wearing a different mask. They called it the Sky Crane. After the heat shield had done its work, and a supersonic parachute had slowed the spacecraft as much as it could, a rocket-powered platform, the Sky Crane, would separate from the backshell, fire its engines to arrest the remaining descent, hover in mid-air, and then lower the rover to the surface on cables, like a giant robotic helicopter delivering a package. Once the rover touched down and the cables went slack, the Sky Crane would fly itself away and crash at a safe distance. The whole sequence from parachute deployment to touchdown took about 7 minutes. And it worked, both times, which is genuinely astonishing when you think about it, because every single component had to function correctly in sequence, with no human hand to intervene if anything went wrong. But here is the problem that makes every Mars engineer lose sleep when they contemplate a crewed mission. Curiosity weighs about 900 kilograms. Perseverance weighs about 1,025 kilograms. A crewed Mars lander, with its life support systems, its fuel reserves, its landing engines, its habitat components, its emergency systems, everything 2 to 6 human beings need to survive on the surface, would likely need to weigh somewhere in the range of 20 to 40 metric tons, depending on the mission architecture. Some proposals push higher. That is not a factor of 2 or 3 heavier than our most successful robotic landers. It is a factor of 20 to 40, and the physics of landing on Mars do not scale linearly. The problem gets dramatically harder as mass increases because the atmosphere's limited braking capacity becomes an even smaller fraction of what you need. The parachutes that slowed Curiosity and Perseverance, which were themselves the largest supersonic parachutes ever deployed, each about 21 meters across, and each subjected to forces of roughly 65,000 kilograms during inflation, would be nowhere near sufficient for a crewed lander. The aerodynamic forces involved, the heat loads, the structural requirements, all of it balloons in ways that push against the limits of current materials and engineering. NASA's Mars landing studies have consistently identified this as one of the hardest unsolved problems in the entire architecture of a human Mars mission. SpaceX's approach with Starship takes a fundamentally different philosophy. Rather than using parachutes at all, Starship is designed to perform what is called a belly flop maneuver, orienting itself horizontally to maximize atmospheric drag during entry, using its body itself as a kind of blunt aeroshell, and then flipping vertical at the last moment to fire its engines for a propulsive landing. This approach sidesteps the parachute scaling problem by relying almost entirely on propulsion for the final deceleration. But it introduces its own challenges. The fuel required for a full propulsive landing on Mars is enormous, and bringing that fuel from Earth is extraordinarily costly in terms of mass. SpaceX's architecture involves producing fuel on Mars itself, using a process called in-situ resource utilization, specifically manufacturing liquid oxygen and liquid methane from the Martian atmosphere and subsurface water ice. The chemistry works. The Sabatier reaction for methane production and electrolysis for oxygen production are well understood, but doing it at scale reliably on an alien planet before anyone has landed, that is an engineering and logistical challenge of a completely different order. And all of this is before we even get to the question of where exactly you land. Choosing a landing site for a crewed Mars mission is a decision with life or death consequences. You need flat terrain to avoid tipping on landing. You need proximity to water ice, because water is the most important resource on Mars. It can be split into hydrogen and oxygen for fuel and breathable air, and it provides radiation shielding when used in wall panels. You need to avoid areas with high concentrations of perchlorates in the soil, which are toxic to humans. You need to consider dust storm patterns, because Mars experiences regional and global dust storms that can reduce solar power generation dramatically for weeks or months. The global dust storm of 2018, which ultimately ended the Opportunity rover's mission, lasted for months and reduced sunlight to a fraction of normal levels across vast swaths of the planet. You need access to scientifically interesting terrain for exploration. You need to be close enough to the equator to maximize solar power, but potentially far enough from it to access ice deposits. Every one of these requirements pulls in a slightly different direction, and the overlap between all of them is smaller than you would hope. Current leading candidate sites include regions near the Hellas Planitia Basin, various locations in the mid-latitudes where radar data from the Mars Reconnaissance Orbiter has confirmed the presence of near-surface water ice, and areas near the Jezero crater where Perseverance is currently operating, a location chosen precisely because it shows evidence of ancient water activity and represents some of the most scientifically valuable terrain on the planet. Every one of these sites has trade-offs. Every one of them presents unique dangers. And when that lander finally touches down, if it touches down, the crew will have approximately 90 seconds to assess whether the landing was nominal before beginning the post-landing checklist. 90 seconds to determine whether their spacecraft is intact, upright and functional, because if the landing goes wrong, if the lander tilts beyond its recovery threshold, if a landing leg fails, if an engine shuts down a fraction of a second too early or too late, the options are limited in ways that do not bear thinking about too carefully. There is no rescue mission waiting in orbit. The ascent vehicle that will eventually carry them back to orbit either came with them or, in some architectures, was sent ahead and is waiting on the surface, which introduces its own terrifying dependency. What if the ascent vehicle was damaged by a dust storm during the years it waited? What if its fuel production systems underperformed? What if it tipped over on a slope? The crew descending in the lander would have no way of knowing until they were already committed to the landing. Here is what I find most extraordinary about all of this, and I mean extraordinary in the sense of genuinely, deeply moving, not just technically impressive. Every rover we have ever landed on Mars, every lander, every probe, each one represents the distilled effort of thousands of human beings working for years, pouring their expertise and their passion and their late nights into a machine they could never touch again once it left Earth. And when those machines landed successfully, when the signal came back and the data started flowing and the first images appeared on screens in mission control, the tears you saw on those engineers' faces were real. They were the tears of people who understood exactly how close to failure they had come, how narrow the margin was, how much had to go right. Now imagine that, but with people inside. Imagine being one of those engineers, watching the telemetry from a crewed lander during those 7 minutes of terror, knowing that the data you are seeing is already 7 to 22 minutes old, knowing that whatever happened has already happened, that the people inside are already safe or already lost, and you are just waiting to find out which. That is the weight of this mission. And it sits on the shoulders of everyone involved in building it, but let us say the landing works. Let us say those 7 minutes pass, the retro rockets fire at exactly the right moment, the legs deploy cleanly, the spacecraft settles onto Martian soil at a gentle velocity, and the crew's voices come crackling back over the radio, delayed by the speed of light but unmistakably alive. Let us say that happens. What greets them outside that hatch is not a welcome. It is not a comfortable environment waiting to be explored. It is one of the most hostile surfaces in the solar system. And the specific ways in which Mars wants to kill you, quietly, chemically, radiologically, thermally, are as varied as they are relentless, because we have not yet talked about the soil. We have not talked about what happens if you breathe the air, even for a moment. We have not talked about the temperature swings that happen every single day on the Martian surface, swings so extreme that the engineering challenge they pose is almost comical in its severity. We have not talked about the dust, not just as an inconvenience, not just as a power management problem, but as a biological and mechanical threat that permeates every aspect of surface operations. The surface of Mars is where this story gets its sharpest edges, and that is where we are going next. The hatch opens after 6 to 9 months of recycled air, of the sterile metallic smell of a pressurized spacecraft, of the faint hum of life support systems that never quite disappears no matter how deeply you sleep. After all of that, the first human being to step onto the surface of Mars will press their gloved hand against that hatch, push it outward, and look out at a world that no human eye has ever seen up close. And what they will see is beautiful. Genuinely, heartbreakingly beautiful. A vast, rusty plain stretching to a curved horizon. A sky the color of a bruised peach, salmon pink during the day, shifting toward electric blue near the sun. Dust devils spinning lazily across the distance. Rocks worn smooth by billions of years of wind in a landscape that has not known rain in perhaps 3 billion years. It will feel, in that moment, like the most profound thing a human being has ever done. And it will be, unambiguously, historically, cosmically, it will be the most significant footstep our species has ever taken. And the ground beneath that boot will be trying to kill them, not dramatically, not immediately, not in the way that a monster in a film jumps out and announces itself, but quietly, chemically, persistently, in the way that the most dangerous things in nature always work. Through processes so subtle they are invisible to the human senses, operating at the molecular level, accumulating over weeks and months until the damage becomes impossible to ignore. Let us start with the soil. Because Martian soil, scientists call it regolith, which is the technical term for the loose surface material covering a rocky body, is not like Earth soil in any meaningful way. Earth soil is alive. It is teeming with bacteria, fungi, organic matter, decomposing material, the biological output of billions of years of life, reshaping the surface chemistry of this planet. Martian regolith is the opposite of that. It is the product of billions of years of geological and chemical processes operating in the complete absence of life, as far as we know, and the result is a substance that is, in several specific ways, acutely hostile to biology. The most significant chemical threat in Martian regolith is something called perchlorates. These are salts of perchloric acid, specifically compounds containing the perchlorate ion, which is chlorine bonded to 4 oxygen atoms. On Earth, perchlorates are considered environmental contaminants. They interfere with the thyroid gland's ability to absorb iodine, disrupting the production of thyroid hormones that regulate metabolism. At sufficient concentrations and with sufficient exposure, they are toxic. Regulatory agencies set strict limits on perchlorate levels in drinking water precisely because of these health effects. On Mars, perchlorates are not a contaminant. They are a fundamental component of the soil. The Phoenix lander, which touched down in the northern polar region of Mars in 2008, was the first mission to definitively detect perchlorates in Martian soil, finding concentrations of roughly 0.5 to 1% by weight. Subsequent missions have detected them across multiple locations, suggesting they are globally distributed. The Curiosity rover has detected them in Gale Crater, thousands of kilometers from where Phoenix landed. This is not a local quirk of Martian chemistry. It appears to be a planet-wide feature produced by ultraviolet radiation breaking down chlorine-containing compounds in the atmosphere and surface over geological timescales. What this means for a human crew on the surface is deeply concerning. Perchlorate-laden dust will coat everything. It will settle on spacesuits during every EVA, every extravehicular activity, every excursion outside the habitat. It will be tracked in on boots and equipment. It will find its way into air filtration systems, and if it finds its way into the habitat atmosphere in sufficient quantities, into food preparation areas, into water recycling systems, the exposure pathways are numerous and difficult to fully eliminate, even with rigorous contamination protocols. But perchlorates have another property that makes them particularly troubling in the Martian context. At elevated temperatures, and some Mars habitat systems, some life support components, some equipment will generate heat. Perchlorates can become strong oxidizers. They can react vigorously with organic material, human organic material. And while a perchlorate-rich soil is already a health concern at ambient temperatures, a perchlorate-contaminated habitat environment that experiences a fire or a thermal event becomes something significantly more dangerous. Jennifer Wadsworth and Charles Cockle, researchers at the University of Edinburgh, published a study in 2017 in Scientific Reports demonstrating something particularly striking. When they combined Martian perchlorate concentrations with ultraviolet radiation levels representative of the Martian surface, they found that the combination was bactericidal. It killed bacteria 700 times more effectively than ultraviolet radiation alone. The perchlorate, when activated by UV, produces highly reactive oxygen species that destroy organic molecules with extraordinary efficiency. On an unprotected Martian surface, life as we know it faces not just one hostile factor, but a synergistic combination of factors that amplify each other's lethality. For the human crew, this means the surface itself, the ground they walk on, the dust that swirls around their boots, the particles that settle on every surface exposed to the Martian environment, is not merely inert rock. It is a chemically active, biologically hostile material that requires constant vigilance and rigorous management protocols every single day of their surface stay. And then there is the dust itself, independent of its chemical properties. Simply as a physical material, Martian dust is a profound engineering and biological challenge. It is extraordinarily fine, particles so small they remain suspended in the thin atmosphere for months following major dust storms. It is electrostatically charged, meaning it clings to surfaces with a tenacity that simple brushing cannot overcome. It has already demonstrated its ability to end robotic missions. Opportunity's solar panels were gradually covered over years of operation, and the global dust storm of 2018 reduced incoming sunlight to the point where the rover could no longer power itself. The InSight lander's solar panels suffered similar degradation, ultimately contributing to the mission's end in December of 2022. For a crewed mission, dust management is not just a power generation concern, it is a life support concern. Spacesuits worn during EVAs will collect dust on every surface, the visor, the joints, the seals around the helmet. Getting back into the habitat through an airlock without tracking significant quantities of perchlorate-laden dust requires engineering solutions, dust removal systems, airlock designs that minimize contamination transfer, that are still being actively developed and tested, and even the best system will not achieve perfect separation. Over months of surface operations, dust accumulation inside the habitat is essentially inevitable. The health implications of chronic, low-level exposure to Martian dust, its particle size, its chemical composition, its potential mineralogical content, including materials like silicates, that can cause pulmonary damage, are not yet fully characterized. We know from terrestrial analogues that fine mineral dust is dangerous to breathe. Silicosis, caused by inhaling crystalline silica dust, is a well-documented occupational hazard in mining and construction. The Moon provided an early warning about the dust problem in space environments. Apollo astronauts reported that lunar dust was extraordinarily abrasive and clingy, damaging suit seals and getting into everything. Lunar dust particles are jagged and angular because, without weather or water to smooth them, they never get worn down. Martian dust has been exposed to more weathering processes and is generally considered less acutely abrasive than lunar dust, but it has its own chemical profile that makes long-term inhalation exposure a serious concern. Now let us talk about temperature. Because the temperature swings on the Martian surface are something that requires a moment to fully absorb, because they are so extreme compared to anything in human experience that they almost sound like fiction. Near the equator on Mars, a summer day might reach a surface temperature of around 20 degrees Celsius in the early afternoon, not unlike a cool spring day in a temperate climate on Earth. That sounds almost hospitable, but that same location on that same day will plunge to approximately -73 degrees Celsius by the pre-dawn hours. That is a daily temperature swing of roughly 93 degrees in a single day, in a single location. On Earth, some of the most extreme continental climates, parts of Siberia, parts of the Canadian Arctic, might experience annual temperature ranges of 60 to 70 degrees between their coldest winters and warmest summers. Mars does that every 24.6 hours. What this means for engineering is staggering. Every piece of equipment on the surface, every structural component, every seal, every joint, every cable, every piece of electronics has to be designed to survive repeated thermal cycling through a 90-degree range, day after day, for the duration of the mission. Materials expand and contract with temperature changes. Seals that flex and compress 1,000 times are seals that eventually fail. Lubricants that work at 20 degrees may become viscous or solidify at -73. Batteries lose capacity in the cold and may not be able to deliver the power needed to heat the very systems that keep the crew alive during the long Martian night. The Martian night, incidentally, lasts about 12 hours near the equator, slightly more or less depending on season and latitude. 12 hours during which solar power generation is zero. 12 hours during which the habitat's thermal management systems are fighting to maintain a livable interior temperature against an exterior that is brutally, lethally cold. The thermal insulation requirements for a Mars habitat are extraordinary, and every centimeter of insulation adds mass that had to be launched from Earth at enormous cost. And speaking of the habitat, the structure that will shelter the crew for what could be anywhere from a few hundred days to several years, depending on the mission architecture, let us talk about what that actually has to be and what happens if it fails. The Mars habitat will be the only barrier between a living human being and an environment that is simultaneously too cold, too irradiated, too chemically hostile, and too thin in atmosphere to sustain consciousness for more than about 2 minutes. The atmospheric pressure on the Martian surface is roughly 600 pascals, less than 1% of Earth's sea level pressure of 101,300 pascals. At that pressure, the moisture in your eyes and mouth would begin to evaporate. Your blood would not boil. That is a common misconception, but without a pressure suit or pressurized habitat, the oxygen in your blood would rapidly become insufficient to maintain brain function. Unconsciousness would follow within seconds, death within minutes. The habitat, then, is not a convenience. It is the difference between alive and dead maintained continuously without a single critical failure for the entire duration of the mission, and habitats can fail, seals can degrade. Micrometeorite impacts. Mars lacks Earth's thick atmosphere to burn up small impactors, and its proximity to the asteroid belt means the flux of small debris is higher than Earth experiences, can puncture walls. Equipment malfunctions can compromise pressure integrity. The most frightening failure scenario is a slow leak, a small puncture or seal degradation that loses pressure gradually enough to evade immediate detection, but fast enough to become life-threatening before it is identified and addressed. NASA and mission planners spend enormous resources on habitat integrity monitoring, on redundant seals and pressure sensors, on emergency patch kits and rapid response procedures. But the history of space exploration includes enough unexpected failures. The Apollo 1 fire that killed 3 astronauts on the launch pad, the Challenger disaster, the Columbia tragedy, to make any claim of zero failure probability ring hollow. Space is unforgiving, and Mars is farther from help than any environment humans have ever operated in. There is something I want to pause on here, though, because we have been cataloguing dangers, and every one of them is real, every one of them is documented, every one of them demands our full seriousness. But there is another dimension to this story that is equally real and equally important. Human beings have faced impossible environments before. We have crossed oceans in wooden boats with no instruments beyond stars and intuition. We have climbed mountains that killed experienced climbers without oxygen, without modern gear, driven by something that defied rational self-preservation. We have descended into the deepest parts of the ocean in vessels that represented the absolute limit of what engineering could achieve at the time. And we did all of those things not because survival was guaranteed. It was never guaranteed, but because the pull of the unknown was stronger than the pull of safety. The first humans to stand on the surface of Mars will know exactly what they are risking. They will have read every study, absorbed every risk assessment, run every simulation, and they will go anyway. Because that is what we do, that is what we have always done, and in a universe that is 4 billion years old, on a planet that formed from the same stellar debris as every other rock and ocean and living thing in this solar system, there is something genuinely moving about the fact that the matter of the cosmos has arranged itself into creatures curious enough to cross the void between worlds. Carl Sagan wrote that we are a way for the cosmos to know itself. The first footsteps on Mars will be the cosmos taking another step toward knowing itself through us. But, and I want to be very clear about this, knowing is not the same as safe. And what waits for that crew beyond the habitat walls, beyond the dust and the perchlorates and the temperature extremes, is something we have not yet discussed. Something that operates on a timescale longer than a single EVA, longer than a single storm season. Something that accumulates silently over the months and years of a surface stay, and that represents, in the judgment of many researchers, the single greatest long-term health threat to any human being who spends significant time on the Martian surface. We are talking about radiation, not the transit radiation we discussed in Part 1, though that continues to accumulate during surface operations. We are talking about the surface radiation environment, specifically, what it consists of, what it does to the human body over time, and what the data from Curiosity's radiation assessment detector, the most detailed surface radiation measurements ever taken on another planet, actually tells us about the dose a human crew would receive during an extended stay. The numbers are not comfortable, so let's look at them in a practical way. There is an instrument sitting inside the belly of the Curiosity rover right now, as you watch this video, quietly doing something no piece of hardware has ever done before on another planet. It is called the Radiation Assessment Detector, RAD for short, and it has been measuring the radiation environment on the surface of Mars continuously since Curiosity landed in Gale Crater in August of 2012. Every hour of every day, through dust storms and solar flares and the long cold Martian nights, RAD has been counting particles, measuring energies, building a dataset that for the first time in history gives scientists a real empirical picture of what a human body would experience if it stood on the Martian surface for an extended period. The team behind RAD, led by physicist Don Hassler of the Southwest Research Institute, published their first comprehensive surface radiation analysis in the journal Science in 2013, and the numbers they reported have been shaping, and in some cases sobering, the conversation about human Mars exploration ever since. Here is what they found. On the surface of Mars, the average radiation dose rate measured by RAD is approximately 233 microsieverts per day. That translates to roughly 0.23 millisieverts per day. Over the course of a 500-day surface stay, which represents a plausible minimum for a conjunction-class mission where the crew stays on Mars until the planets align favorably for a return journey that accumulates to approximately 117 millisieverts just from surface operations. Add that to the roughly 300 millisieverts from the transit to Mars, and the roughly 300 millisieverts from the return transit, and you are looking at a total mission radiation dose somewhere in the range of 700 millisieverts for the entire mission. To put that in context, NASA's current career radiation limit for astronauts is 600 millisieverts. A single Mars mission under this estimate would exceed that limit by roughly 17%, and that is before accounting for any solar particle events during the surface stay, which could add significant additional dose in a short period of time. Now, it is important to be precise here, because radiation risk communication is an area where imprecision causes real confusion. The numbers above are estimates based on the best available data, and actual mission doses would depend on a huge number of variables: the specific trajectory, the solar activity during the mission, the shielding design of the spacecraft and habitat, the duration of the surface stay, the specific location on Mars. Some of these variables can be optimized to reduce dose, others are simply outside human control. But the fundamental reality that a Mars mission represents a radiation exposure significantly above any previous human spaceflight mission is not in dispute among researchers in this field. What does that radiation actually consist of? On the Martian surface, it is a combination of two things. The first is the galactic cosmic rays we discussed in Part 1, those high-energy particles streaming in from beyond our solar system, originating from supernovae and other violent cosmic events across the galaxy. On the Martian surface, these particles arrive from above, having passed through the thin Martian atmosphere, which provides only minimal shielding. Mars has no global magnetic field to speak of. It lost the bulk of its magnetic field billions of years ago, when its core cooled and solidified, shutting down the dynamo effect that generates a protective magnetosphere. Without that field, galactic cosmic rays have a largely unobstructed path to the surface. The second component is something specific to Mars that is not a factor on the open transit through space. When those high-energy galactic cosmic rays slam into the Martian soil, they do not simply stop. They interact with the atoms in the regolith and produce secondary radiation, a spray of neutrons, gamma rays, and other particles that scatter upward from the ground. This means that on the Martian surface, radiation is not just coming from above, it is coming from below as well, bouncing up from the soil beneath the crew's boots, the habitat floor, the ground under the rovers, the regolith surrounding the base. All of it is a source of secondary radiation that adds to the total dose. This upward component, called albedo radiation, actually makes the problem more complex to shield against. You can put radiation shielding in the walls and ceiling of a habitat relatively straightforwardly. Shielding the floor adequately or building a habitat in such a way that the crew is protected from radiation coming from multiple directions simultaneously is a significantly harder engineering problem and adds mass that compounds every other constraint in the mission architecture. One of the most promising mitigation strategies that has been seriously proposed is building habitats underground. Mars has extensive lava tube systems, vast underground tunnels carved by ancient volcanic activity, similar to lava tubes found in places like Hawaii and the Canary Islands on Earth, but potentially on a much larger scale. A 2017 study using data from the Charad radar sounder aboard the Mars Reconnaissance Orbiter suggested that some Martian lava tubes could be large enough to contain entire cities. If a crew could establish their primary habitat inside a lava tube or under several meters of regolith, the rock and soil above them would provide substantial shielding against both galactic cosmic rays and solar particle events, dramatically reducing their daily dose. The depth required for meaningful shielding is actually not as great as you might imagine. Studies suggest that roughly 2 to 3 meters of Martian regolith, which is relatively porous and rich in hydrogen-containing compounds in some locations, a factor that helps with neutron shielding, could reduce the surface radiation dose by a factor of somewhere between 2 and 10, depending on the specific composition and the type of radiation being considered. A habitat built under that much cover would transform the radiation environment from a serious ongoing health threat to something considerably more manageable. But getting to a lava tube, establishing infrastructure inside it, living and working in an underground environment for months or years, that introduces its own cascade of engineering and psychological challenges. Underground habitats require artificial lighting for every waking hour. They create a more extreme version of the confinement we discussed in Part 3. They require careful monitoring for radon gas, which can accumulate in enclosed underground spaces, and is itself a radiation hazard and reaching the surface for EVAs. Every time the crew needs to go outside requires traversing the most radiation-intense environment on the planet. The surface radiation picture also changes dramatically during solar particle events. When the sun releases an intense burst of energetic particles, During a major solar flare or a coronal mass ejection, the dose rate on the Martian surface can increase by orders of magnitude in a matter of hours. Unlike on Earth, where the magnetic field deflects most of these particles, and unlike on a spacecraft with a dedicated storm shelter, a crew caught in the open on the Martian surface during a major solar particle event faces acute radiation exposure that, in the most severe events, could deliver a dangerous dose in a matter of hours. The solar particle event of August 2003, the so-called Halloween storms, was one of the most intense on record. Had astronauts been on the Martian surface during that event, estimates suggest they could have received a radiation dose equivalent to several years of normal surface exposure in a matter of days. A dose at that level crosses from the territory of elevated cancer risk into the territory of acute radiation syndrome, the direct, immediate biological damage caused by high radiation doses that produces symptoms ranging from nausea and vomiting to hair loss, immune system collapse, and at the highest doses, death. The Mars crew will need to maintain continuous situational awareness of solar weather. They will need reliable forecasting of solar events, which has improved dramatically in recent decades but remains imperfect, particularly for the most extreme events that have the least historical precedent, and they will need rapid access to a shielded refuge any time a major event is detected, a location they can reach in minutes, not hours, because the particle front from a solar flare can travel from the Sun to Mars in as little as 20 to 30 minutes during the most energetic events. Planning, drilling, and executing that emergency response repeatedly, reliably, under the accumulated fatigue of months on the surface is one of the operational challenges that Mars mission architects think about at 3 in the morning. Now, here is something that the radiation story opens up into when you zoom out far enough to see the bigger picture. And I want to take a moment here because this is one of those places where the science connects to something genuinely profound. Mars lost its magnetic field billions of years ago. We know this partly from the magnetized rocks in the ancient southern highlands, rocks that were magnetized when Mars still had a global field and have retained that record ever since, like a planetary fossil of a protective shield that no longer exists. The leading explanation is that Mars's smaller size compared to Earth meant its interior cooled faster. The convection currents in the liquid iron core that generate a magnetic field through the dynamo effect gradually weakened and stopped. And with that shutdown, the solar wind began stripping away the Martian atmosphere, a process that continues today, slowly but measurably, as NASA's MAVEN spacecraft has been documenting since it entered Mars orbit in 2014. In other words, the radiation environment that makes Mars so hostile to life today is not a static, eternal feature of the planet. It is the end state of a process, a planetary-scale tragedy that unfolded over billions of years. Mars may once have had a thicker atmosphere, liquid water on its surface, and a magnetic shield not unlike Earth's. It may once have been a place where life, simple, microbial life, the kind that was probably already present on Earth at the same time, could have existed. The question of whether it did is one of the most electrifying open questions in all of science, and Perseverance is searching for exactly that answer in the ancient lakebed of Jezero crater right now. The crew that lands on Mars will be walking on a world that might have once been alive. They will be searching for traces of that ancient life in the rocks and the soil, in the chemistry of ancient riverbeds and lake shores frozen in geological time. And they will be doing it while a radiation environment that would have been alien to early Mars slowly accumulates in their bodies. There is something almost elegiac about that. Something that makes the mission feel not just like an adventure, but like a kind of reckoning. Humanity reaching toward a world that the universe has been quietly dismantling for billions of years. But the radiation is not the only long-term health challenge of an extended Mars surface stay, because we have not yet talked about what Martian gravity, or rather, the significant lack of it compared to Earth, does to a body over months and years on the surface. We touched on microgravity during the transit in Part 2. But Mars gravity, at 38% of Earth's, is not zero. It is a genuine gravitational environment. You will have weight on Mars. You will be able to walk, albeit with a bouncy, loping gait that will feel deeply strange for the first few days. You will be able to put things down on surfaces and have them stay there. But 38% is not 100%. And the question of whether 38% of Earth gravity is sufficient to prevent the bone loss, the muscle atrophy, the cardiovascular changes, and the fluid shift effects we discussed in Part 2, or whether it simply slows them down relative to full weightlessness, still allowing them to accumulate over a long surface stay, is a question that science cannot yet definitively answer. We have never had a human being spend extended time in a 38% gravity environment. We have data from zero gravity on the International Space Station. We have data from 100% gravity on Earth. We have almost nothing from the range in between, because there is no place in our current infrastructure where that experiment can be conducted. No rotating habitat that simulates partial gravity, no long-duration mission in an environment like Mars before Mars itself. This gap in our knowledge is not a minor footnote. It is a fundamental uncertainty that sits at the heart of every long-term Mars colonization proposal. Elon Musk has spoken about wanting to establish a self-sustaining city on Mars with a population of 1 million people. But if Martian gravity turns out to be insufficient to maintain human bone density and cardiovascular health over years, if living on Mars produces the same kind of progressive physical deterioration as living in zero gravity, just more slowly, then the vision of humans thriving on Mars long-term becomes dramatically more complicated. Children born on Mars, if they were conceived and carried to term in Martian gravity, an environment that would itself present extraordinary challenges to pregnancy and fetal development, might not be physically capable of ever visiting Earth. They might be, in the most literal biological sense, Martians, adapted to a gravity well that their bodies had never left. We do not know if that would happen. We genuinely do not know. And that uncertainty is both humbling and fascinating in equal measure. What we do know, what the data and the physics and the biology tell us with confidence, is that the first humans to spend an extended period on Mars will be accumulating health effects from multiple simultaneous stressors. Radiation, gravity, dust, chemical exposure, psychological pressure, disrupted sleep, altered circadian rhythms from a Martian day that is 24 hours and 37 minutes long rather than Earth's 24 hours, a difference small enough to seem trivial, but large enough over months to create a persistent low-level circadian misalignment that affects sleep quality, cognitive performance, and mood. Each of these factors in isolation is manageable. In combination, over a mission lasting years, they create a health landscape that is genuinely unprecedented in human medicine. The crew's physician, because every Mars crew will include someone with medical training, likely with the capability to perform surgery and manage acute medical emergencies, will be practicing medicine in a context that has no parallel in the history of the profession, with a communication delay that makes real-time consultation with Earth-based specialists impossible, with a pharmaceutical supply limited to what they brought from home, with surgical capabilities constrained by the size and equipment of the Habitat medical bay. The medicines and medical equipment the crew carries will be determined before launch. They cannot order more. If someone develops a condition that requires a medication not in the inventory, if someone needs surgery beyond the crew's capability, if someone develops cancer, if someone has a psychiatric crisis that cannot be managed with the psychological support tools available. The options are limited in ways that are deeply uncomfortable to think about, but absolutely necessary to plan for. This is the reality of the first Mars mission, not a triumphant parade across an alien landscape, though that will happen too, and it will be extraordinary, but also a daily negotiation with a planet that is indifferent to human survival, using tools and training and sheer human determination to stay alive long enough to do the science, gather the knowledge, and if everything goes right, make it home. And that return journey, the ascent from Mars, the transit back to Earth, the re-entry into Earth's atmosphere, brings its own terrifying challenges that we have not yet begun to discuss. Because getting off Mars is in some ways even harder than getting there, and the state of the crew's bodies after months or years on the surface makes every phase of that return more dangerous, not less. There is a particular kind of psychological phenomenon that explorers and researchers who study isolated environments have documented repeatedly across dozens of different contexts. From Antarctic expeditions to submarine deployments to long-duration spaceflight simulations, it is called goal fixation, and it describes something deeply human, something almost inevitable when a person has been pushing toward a single objective for a very long time under very difficult conditions. The goal, reaching it, completing it, surviving to the end of it, becomes so dominant in the mind that everything beyond it becomes abstract, unreal, hard to plan for with the same emotional urgency as the mission itself. For the first Mars crew, the goal is getting to Mars, surviving on Mars, doing the science, planting the flag in the metaphorical sense of proving that it can be done. And somewhere in the accumulated exhaustion and triumph of achieving all of that, the return journey can begin to feel almost like an afterthought, like something that will sort itself out. Like the hard part is over, it is not over. In several critical ways, the hardest part is just beginning. Getting off the surface of Mars requires an ascent vehicle, a rocket capable of lifting the crew from the Martian surface to orbit, where they will rendezvous with the transit vehicle that will carry them back to Earth. And the ascent vehicle, in every serious mission architecture that has been proposed, is one of the most constrained, most critical, and most unforgiving pieces of hardware in the entire mission stack. It has to be light enough to have been landed on Mars in the first place, either with the crew or years earlier as part of a pre-deployed infrastructure. It has to carry enough propellant to achieve Mars orbit, which requires reaching a velocity of roughly 3.5 kilometers per second. And it has to work perfectly the first time, with no possibility of a second attempt if something goes wrong during the ascent burn. On Earth, if a rocket fails on the launch pad or during ascent, there are escape systems, abort procedures, ocean recovery options. The history of spaceflight includes close calls where abort systems saved lives. The Soyuz MS-10 mission in October of 2018 experienced a booster failure 2 minutes after launch, and the two-person crew was saved by an automatic abort system that pulled their capsule away from the failing rocket and landed them safely on the Kazakh steppe. They were shaken but alive. The abort worked because Earth was right there. Gravity was familiar. Recovery teams were on standby. On Mars, an abort during ascent means coming back down to the surface, which might be survivable if the ascent vehicle can achieve a controlled landing back on the surface. But the ascent vehicle, by design, is optimized for going up, not for coming back down. It will be stripped of everything not essential for the climb to orbit. Its landing capability, if it has any at all, will be severely limited. A failed ascent on Mars, in most scenarios, is not a situation with a good outcome, and the propellant situation for the ascent vehicle is one of the most complex logistical challenges in the entire mission. The two most seriously proposed propellant combinations for a Mars ascent vehicle are liquid oxygen and liquid methane. The combination SpaceX uses for its Raptor engines, and liquid oxygen and liquid hydrogen. Both require cryogenic storage, meaning they must be kept at extraordinarily low temperatures to remain liquid. Liquid oxygen needs to be kept below -183 degrees Celsius. Liquid hydrogen below -253 degrees Celsius, maintaining those temperatures on the Martian surface with its wild daily temperature swings for the months or years between when the ascent vehicle is pre-deployed and when the crew actually needs to use it, requires active refrigeration systems that consume power continuously and can themselves fail. SpaceX's in-situ resource utilization approach, manufacturing propellant on Mars from local resources rather than bringing it from Earth, is genuinely elegant in concept and potentially transformative if it can be made to work reliably at scale. The chemistry is sound. Carbon dioxide from the Martian atmosphere, combined with hydrogen extracted from water ice in the subsurface, can be converted into methane and water through the Sabatier reaction. Electrolysis of the water produces oxygen. Both products can be liquefied and stored as propellant. The MOXIE experiment aboard the Perseverance rover, Mars Oxygen in Situ Resource Utilization Experiment, has already demonstrated oxygen production from the Martian atmosphere on a small scale, producing roughly 6 to 10 grams of oxygen per hour during its operational runs between 2021 and 2023. This is a proof of concept, not a production system. Scaling that to the hundreds of metric tons of propellant needed for a crewed ascent vehicle is an engineering challenge of an entirely different magnitude. But the fact that it has been demonstrated at all on the actual surface of Mars is one of the most quietly significant achievements in the history of space exploration. Let us say it all works. The propellant has been produced. The ascent vehicle has been maintained in working order through years of surface operations. The crew has completed their mission. They have collected samples, conducted experiments, survived the radiation and the dust and the isolation. They board the ascent vehicle, strap in and ignite the engine. The burn lasts roughly 5 to 7 minutes. During that time, the crew experiences the return of sustained acceleration, G-forces pressing them back into their seats for the first time in months or years. And this is where the physiological deterioration we have been discussing throughout this entire video suddenly stops being a background concern and becomes an acute, immediate physical reality. Bodies that have spent extended time in Martian gravity, 38% of Earth's, will have adapted to that environment. The cardiovascular system will have adjusted its output. The muscles will have calibrated their strength to a reduced gravitational load. The fluid distribution in the body will have found a new equilibrium, and now, in the span of a few minutes, those bodies are being subjected to the stresses of rocket ascent, not the 1G of Earth's surface, but the higher forces of powered flight, potentially 2 to 3 Gs during peak acceleration. For crew members in peak physical condition, this is manageable. For crew members who have spent a year or more on Mars, who may have experienced radiation-related health effects, vision changes from SANS, residual bone density loss despite exercise protocols, cardiovascular deconditioning, the physiological stress of ascent is a genuine medical concern. Every crew member's body will respond differently based on their individual health trajectory during the surface stay. And the flight surgeon on the crew will be monitoring vital signs closely during ascent, with very limited ability to intervene if someone's cardiovascular system does not respond well to the sudden return of high acceleration loads. The ascent to Mars orbit, if everything goes correctly, places the crew in a highly elliptical orbit that must then be matched with the waiting transit vehicle. This orbital rendezvous, docking with the Earth return vehicle in Mars orbit, is another critical point of failure. Orbital rendezvous requires precise navigation, functioning propulsion systems on both vehicles, and a compatible docking interface. The International Space Station has been conducting orbital rendezvous operations routinely for decades, and it still requires careful preparation and occasionally experiences anomalies. Doing it in Mars orbit, with limited communication support from Earth, with a crew that has been living on the surface for a year or more, adds layers of complexity to a procedure that is never routine, regardless of how many times it has been done. Once safely aboard the Earth return vehicle, the crew faces the transit home. And this is where the radiation accounting we discussed in Part 6 becomes particularly stark, because the return trip adds another roughly 300 millisieverts to the total mission dose, the same galactic cosmic ray environment, the same solar particle event risk, the same 6 to 9 months of deep space transit that the outbound journey involved. By the time the crew completes the return transit, their total accumulated radiation dose may be approaching or exceeding levels that no human being in the history of space exploration has ever received. And they will be arriving home in bodies that are not the same as the bodies that left. The question of what the return transit does to a body that has already been through a year or more of Martian surface conditions is one that medicine has not yet been able to fully model, because we simply do not have data. We know what 6 months in microgravity does from extensive International Space Station research. We know what the Martian surface environment does to robotic systems. We know what long-duration isolation does to human psychology. But the specific combination, Mars gravity adaptation followed by a return to weightlessness, followed by Earth re-entry, is a physiological sequence that has never been experienced by a human being and cannot be fully simulated before it happens. What we can predict with reasonable confidence is that the readaptation to weightlessness during the return transit will be jarring. Crew members who adapted to Martian gravity over months will experience the same fluid shifts, the same cardiovascular changes, the same disorientation as any astronaut entering weightlessness for the first time, except they will not be experiencing it for the first time. They will be experiencing it in bodies that are already carrying the accumulated burden of the entire mission, and their capacity to bounce back, their physiological resilience, will be significantly reduced compared to what it was at the start. The psychological dimension of the return journey also deserves serious attention, because the end of a Mars mission is not simply a return to normalcy. It is the beginning of a profound readjustment that may take years to complete. Consider what these crew members will have been through. They will have left Earth as private individuals, perhaps well known in their fields, perhaps public figures to some degree, but fundamentally private people with ordinary lives alongside their extraordinary careers. They will return as something entirely different. They will be the first human beings to have set foot on another planet. Every word they speak will be recorded, analyzed, quoted. Every interview, every public appearance, every attempt to process their experience in real time will happen under a global spotlight that has no precedent except perhaps the Apollo astronauts. And even Apollo, as magnificent as it was, lasted days on the lunar surface, not years on Mars. The Apollo astronauts' experiences after their missions tell us something important about this. Neil Armstrong became famously private and reclusive after Apollo 11. Buzz Aldrin has spoken openly about his struggles with depression and alcohol in the years following his moon landing. Michael Collins, who orbited the moon while Armstrong and Aldrin walked its surface, wrote with remarkable candor about the alienation he felt upon returning, not just from the public attention but from the experience itself. from the impossibility of adequately describing what he had seen and felt to people who had not been there. Now imagine that, compounded by years rather than days. By having walked on another world, breathed recycled air in a habitat on an alien planet, watched Earth shrink to a point of light, and returned to find that 2 to 3 years have passed in their absence. Their children are older. Their parents may have died. Their relationships may have changed. The world will have moved on in ways large and small that they were only partially aware of through intermittent, delayed communications. They will step off the recovery vehicle into a gravity that feels crushing after years of living at 38%. Their legs will barely hold them. Their cardiovascular systems will be struggling. Their bones, despite every precaution, will be less dense than when they left. And they will be expected, almost immediately, to begin the debriefs, the medical evaluations, the press conferences, the congressional testimony, the book deals, the documentary interviews. The machine of public attention will want its piece of them before they have had a chance to understand what they themselves have been through. NASA has, to its credit, developed increasingly sophisticated returnee support programs. The psychological support provided to long-duration ISS crew members returning from 6-month missions has improved substantially over the decades. There are structured reintegration protocols, access to mental health professionals with spaceflight experience, carefully managed schedules that protect recovery time in the first weeks after landing. The Mars returnees will presumably have access to even more comprehensive support, but the scale of the readjustment, physical, psychological, social, existential, will be unlike anything any support program has previously been designed to handle. These will be people who have stood on the surface of another world, who have looked up at a sky where Earth is just a star, who have breathed air that was manufactured by machines, who have eaten food that was freeze-dried or grown in small hydroponic systems, who have not felt rain or wind or the smell of a forest for 2 to 3 years. The re-entry into ordinary human life, into grocery stores and traffic jams and social media, and the 1,000 small textures of terrestrial existence will be simultaneously overwhelming and, paradoxically, perhaps a little disappointing, because nothing on Earth, no matter how beautiful, will quite feel as significant as what they left behind. This is not speculation. It is a pattern documented in long-duration Antarctic overwinter teams, in former submariners, in long-duration ISS crew members. Returnees from extreme isolated environments frequently report a period of what researchers sometimes call re-entry syndrome, difficulty reconnecting with social environments, a sense of emotional flatness. In ordinary situations, a longing for the intense sense of purpose and connection that characterized the mission, a feeling that the people around them cannot truly understand what they have experienced. For Mars returnees, this syndrome will operate at a scale and intensity that has no precedent. And yet, and I want to end this part with this thought, because it matters, every person who has ever come back from an extreme environment, from the hardest and most isolating experiences human beings have endured, has also carried something back with them that is impossible to put a number on. A perspective, a depth of understanding about what actually matters, about what the human body and spirit are capable of, about how extraordinary and fragile and precious the world they return to truly is. The Apollo astronauts called it the overview effect, that profound cognitive shift that comes from seeing Earth from space, from grasping its smallness and its beauty and its absolute uniqueness in the visible universe. The Mars crew will have experienced something even more complete than that. They will have stood on a dead world and looked back at the living one. They will have seen with their own eyes what a planet without life looks like, and they will carry that knowledge home in their bones, literally and figuratively, in ways that might ultimately reshape how our civilization thinks about the extraordinary gift of existing on Earth. That return, battered, changed, extraordinary, is not the end of this story, because we have not yet talked about what the first Mars mission means for everything that comes after it, for the missions that will follow, for the question of whether Mars can ever truly become a second home for humanity, for what it would actually take to build something sustainable on that harsh, cold, radiation-soaked world. And we have not talked about something that hovers over all of this, like a question that nobody can quite bring themselves to ask directly. What if someone does not make it back? What if, for the first time in history, human beings die not in the attempt to reach space, but on the surface of another world, in a place so far from home that their bodies cannot be recovered? What does that mean for the mission, for the crew who survives, for the families left behind, for the future of exploration itself? Those are the questions waiting for us to explore now. If you are still watching, you're exactly who we make these videos for. Subscribe and give this a like. Every day we go further, ask harder, and come back with the kind of understanding that actually shifts something in you. Nobody talks about this part, not in the press releases, not in the mission architecture documents that run to thousands of pages of technical specifications, not in the enthusiastic presentations at aerospace conferences where animations show sleek spacecraft gliding gracefully toward a rust-colored horizon, not in the interviews where mission advocates speak with carefully calibrated optimism about timelines and capabilities and the audacity of human ambition. There is a subject that sits at the center of every serious conversation about human Mars exploration, like a stone in still water, and almost everyone finds a way to talk around it rather than directly at it. What happens when someone dies on Mars, not as a hypothetical, not as a philosophical thought experiment, as a genuine operational reality that mission planners have to grapple with, that crew members have to psychologically prepare for, that space agencies and private companies have to have documented procedures for, because the probability that a multi-year Mars mission could be completed without any crew member dying is, when you are being truly honest with yourself, not something that can be assumed away with optimistic engineering. Let us be clear about the numbers, because precision matters here and vagueness does a disservice to the seriousness of the subject. The history of human spaceflight has seen 18 people die in spaceflight-related accidents across roughly 650 individual flights and missions through the era we are discussing. That is a mortality rate that has varied enormously across different phases of the program, higher in the early years, lower as systems matured, spiking with the Challenger and Columbia disasters. The International Space Station has operated continuously since November of 2000, with crew members living aboard for over 2 decades without a fatality in orbit. That record reflects extraordinary engineering, rigorous training, and careful risk management, but the ISS operates in low Earth orbit, roughly 400 kilometers above the surface. Medical emergencies can be, and have been, managed with the option of emergency return to Earth in a Soyuz capsule within hours. The capsules are always docked and always ready. The option exists. It has never had to be used for a life-threatening emergency, but the safety net is there. On a Mars mission, there is no safety net. There is no emergency return capability. If a crew member becomes critically ill or is seriously injured, the options available to the rest of the crew are limited to whatever medical equipment and pharmaceutical supplies they carried from Earth, whatever surgical capability they have been trained to perform in a habitat medical bay, and whatever guidance they can receive from Earth-based medical teams, filtered through a communication delay of up to 44 minutes round trip. If those resources are insufficient, If the condition is beyond the crew's ability to manage, the outcome is determined not by the quality of available medical care, but by the cruelty of physics. Distance has consequences, and on a Mars mission, distance is absolute. The medical scenarios that keep flight surgeons awake at night range from the catastrophic and sudden, a traumatic injury during an EVA, a suit breach, a critical equipment failure, to the slow and insidious, cancer developing mid-mission, a cardiovascular event, an appendicitis, a ruptured disc, a psychiatric crisis that escalates beyond management. Every one of these scenarios has been modeled, at least conceptually, in mission medical planning. And every model arrives at the same uncomfortable conclusion. There will be situations on a long-duration Mars mission where the right answer, from a pure medical standpoint, simply does not exist within the crew's capability to provide. An appendectomy, the surgical removal of an inflamed appendix, one of the most common emergency surgical procedures performed on Earth, has actually been performed in isolated environments, far from surgical facilities. In 1961, a Soviet physician named Leonid Rogozov was stationed at a remote Antarctic research station when he developed appendicitis. With no surgeon available and no way to evacuate in time, he performed surgery on himself, removing his own appendix under local anesthesia with a mirror and the assistance of non-medical colleagues. He survived. It is one of the most extraordinary acts of human determination under pressure ever recorded. But even that story, as remarkable as it is, took place on Earth, with gravity, with a full range of surgical instruments, with the possibility, however remote, of some form of assistance. A Mars crew performing emergency surgery in a habitat medical bay with limited instrumentation in a partial gravity environment on a crew member who has spent a year accumulating the physiological effects we have discussed throughout this video, is operating at the absolute frontier of what medicine can attempt. Now let us go to the scenario that is hardest to sit with. A crew member dies, not from a sudden catastrophic failure that is immediately obvious and irreversible, but from a condition that the crew fought to manage, that they did everything right to address, that simply could not be overcome with the resources available. Someone who was alive and present and essential to the crew, not just operationally but emotionally, as a friend, as a colleague, as the human being they have been living in closest possible proximity to for months or years, is suddenly gone. What happens next? This is a question that has been addressed in mission planning documents in language that is necessarily clinical and procedural, because clinical and procedural is how you make the unbearable manageable enough to plan around. The body would need to be handled in a way that is both respectful and practical, given the constraints of the habitat. Options range from preservation in a dedicated compartment, which introduces psychological and sanitary considerations over a long mission, to, in some mission architectures, the unthinkable but physically straightforward option of returning the remains to the Martian surface through the airlock. There is no good answer, there is only the least bad one given the circumstances, made by people who are already grieving, already exhausted, already carrying the accumulated weight of everything else the mission has demanded of them. The crew that continues after losing a member faces a psychological burden that has almost no parallel in human experience. Combat veterans have lost comrades in the field, but they operated in an environment connected to the broader world, with the possibility of relief, of rotation, of eventually coming home. Antarctic overwinter teams have experienced deaths, though rarely, but with the knowledge that evacuation, however difficult, was conceptually possible for the survivors. The Mars crew would have to absorb the loss, grieve it as fully as human beings can, and then continue operating at the highest possible level of technical competence and psychological stability for months or years more, because the mission does not stop. and the remaining crew's survival depends on maintaining operational effectiveness regardless of what they are feeling inside. Psychologists who study grief in isolated environments note that unresolved grief in confined groups tends to express itself in ways that can be operationally dangerous through displacement onto interpersonal conflicts, through risk-taking behavior, through the kind of emotional numbness that looks like stability but is actually suppression. The crew would need psychological support resources that go far beyond what any previous space mission has provided. Regular sessions with a trained psychologist via the delayed communication link, structured group processing protocols, individual outlets for grief expression, and they would need all of this while continuing to perform complex, demanding, life-critical work every single day. The mission back on Earth would face its own crisis. The death of a crew member on Mars would be the most watched, most analyzed, most politically consequential event in the history of space exploration. Every decision that led to that death, every risk assessment, every funding decision, every engineering trade-off, every training protocol would be examined under the harshest possible public scrutiny. The program that produced it would face pressure from every direction simultaneously, from those who believe the death proves Mars is too dangerous to attempt, from those who believe it proves more funding and more preparation were needed, from the families of every surviving crew member wondering whether their loved ones should be brought home immediately, regardless of mission status. History gives us some guidance here. After the Apollo 1 fire in January of 1967, which killed Gus Grissom, Ed White, and Roger Chaffee during a launchpad test, the Apollo program was grounded for nearly 2 years while the spacecraft was redesigned. After Challenger, in January of 1986, the shuttle program was grounded for 32 months. After Columbia in February of 2003, another 29-month stand-down. Each time the program survived, each time human beings ultimately returned to space. But each time the pause was real, the grief was real, and the political and institutional consequences shaped the program for years afterward. A death on Mars would trigger a response at a scale beyond any of these precedents. Because it would not be a failure of hardware on or near Earth, recoverable and investigable with the full resources of human civilization. It would be a death that happened 225 million kilometers away, that the crew had to manage alone, that the world could do nothing about except watch and grieve and debate. The psychological impact on the global public, on the millions of children watching this mission unfold, on the scientists who dedicated their careers to making it possible, on the engineers who built every component of the spacecraft, would be profound in ways that are genuinely difficult to model in advance. And yet, and this is the part that matters most, the part that cuts through all of the fear and the grief and the procedural language and arrives at something true. None of this is an argument against going. It never has been. Magellan's expedition to circumnavigate the globe lost 4 of its 5 ships and more than 200 of its 270 crew members, including Magellan himself. The survivors who made it back changed humanity's understanding of the world forever, and the knowledge they brought home launched an age of exploration that reshaped civilization. Ernest Shackleton's Endurance expedition lost its ship to pack ice, stranded 28 men on Antarctica for nearly 2 years, and ultimately rescued every single one of them through a feat of navigation and leadership that remains almost unbelievable even today. But it had no guarantee of success when it began. Scott's Terra Nova expedition to the South Pole lost 5 men, including Scott himself, and returned scientific data that contributed to our understanding of Antarctic geology for decades. Exploration has always been this: It has always involved putting human beings in situations where survival was not guaranteed, where the resources were insufficient for the worst case, where the distance from help was the defining feature of the environment, and it has always produced knowledge, perspective, and capability that transformed the civilization that sent the explorers. The first humans to go to Mars will go knowing this history. They will go knowing the risk is real and the outcome is not certain. They will sign the documents, complete the training, say their goodbyes, and climb aboard the rocket anyway, because the alternative, the staying home forever alternative, represents something that our species has never been able to fully choose. We have always sent someone over the horizon. We have always needed to know what was there, but there is a dimension to the Mars mission that goes beyond the history of exploration, beyond the personal courage of the crew, beyond even the scientific value of the mission itself. Because what humanity does on Mars, whether it succeeds or fails, whether everyone comes home or some do not, will shape something fundamental about our long-term future as a species. And that dimension is the one that most profoundly justifies the risk, even as it demands that we take that risk with absolute seriousness and humility. We are a single-planet species. Every human being who has ever lived, every civilization that has ever risen and fallen, every piece of art and music and literature and science that has ever been created, all of it exists on one world, one planet, one pale blue dot, as Carl Sagan famously described it, orbiting an ordinary star in an unremarkable region of a galaxy containing 200 to 400 billion other stars, in a universe containing perhaps 2 trillion other galaxies. And that one world is not invulnerable. The geological record of Earth is a chronicle of catastrophes, mass extinctions driven by asteroid impacts, by volcanic supereruptions, by dramatic shifts in climate. The Chicxulub impactor 66 million years ago ended the reign of the non-avian dinosaurs and reset the course of life on Earth almost completely. A similar event today, or a sufficiently large volcanic event, or a pathogen of sufficient lethality, or any of a dozen other low-probability but non-zero probability catastrophes could do to human civilization what the asteroid did to the dinosaurs. Not necessarily ending all life on Earth, life is extraordinarily resilient and has survived 5 major mass extinctions, but potentially ending the kind of complex, technological, meaning-making civilization that produced mathematics and medicine and music and the very curiosity that drives us toward Mars. Becoming a multiplanetary species is not just an adventure. It is an insurance policy written in human lives and human ingenuity against the possibility of a catastrophe that we cannot predict and cannot prevent from a single world. A self-sustaining human presence on Mars, genuinely self-sustaining, not dependent on resupply from Earth, would mean that whatever happens to Earth, the human story does not end. The library does not burn completely. Something of what we are and what we have learned and what we have created survives somewhere across the void on a world that our descendants would call home. This is the deepest reason for going to Mars. Not the science, though the science will be extraordinary. Not the technological spin-offs, though they will be real. Not national prestige or corporate ambition, though those motivations will certainly play their roles. The deepest reason is that consciousness, self-aware, curious, meaning-making consciousness, is, as far as we know, extraordinarily rare in the universe. We have found no evidence of it anywhere else. We may be alone, and if we are, then the continuation of that consciousness, the preservation of the only known perspective from which the universe can contemplate itself, is worth almost any cost. The first humans to go to Mars will be carrying that weight alongside everything else. Alongside the radiation dosimeters and the emergency medical kits and the freeze-dried food and the carefully scheduled exercise routines. They will be carrying the weight of being the beginning of something. the first chapter of a story that, if it goes well, will continue for as long as there are human beings in this solar system. And what that story looks like, what a genuine long-term human presence on Mars would require, what it would demand of engineering and biology and society and the human spirit, is something we have not yet fully explored in this video. Because surviving the first mission is one thing. Building something that lasts is another entirely. Let us imagine something together. It is 100 years from now, perhaps 150. The exact number does not matter as much as the picture. There is a settlement on Mars, not a temporary outpost, not a research station dependent on supply ships from Earth, but something that has crossed the threshold from outpost to community. There are several thousand people living there, maybe more. Children have been born there. Some of those children have grown up, had children of their own, and never once set foot on Earth. There are schools and medical facilities and workshops and hydroponic farms stretching under pressurized domes or carved into the rock of ancient lava tubes. There is art being made there, music being played, arguments being had about local governance and resource allocation and what kind of society this new world should become. There are cemeteries there because people have lived full lives and died in that place, and their descendants tend the graves of people who chose to leave everything familiar behind and build something new from nothing on a hostile world. That picture, whether it excites you or unsettles you, or both simultaneously, is what the first Mars mission is ultimately pointing toward. It is the destination behind the destination, and the gap between where we are now and that picture is filled with challenges so immense, so varied, so deeply interwoven with each other, that laying them out honestly feels almost like an argument against the whole endeavor. Almost, let us start with the most fundamental question of long-term Mars habitation, the one that everything else depends on. Can human beings actually live on Mars indefinitely, biologically? Not just survive a mission of 2 or 3 years, but genuinely live, grow, reproduce, raise healthy children, age and die in a place where gravity is 38% of what their ancestors evolved under, where radiation levels are far above anything experienced on Earth's surface, where the atmospheric pressure outside the habitat walls is lethal, where every breath of air and every drop of water is produced by machines that require constant maintenance and can fail. The honest answer is that we do not know. And the depth of our not knowing on this question is something that the popular conversation about Mars colonization consistently underestimates. Take reproduction. The question of whether human beings can conceive, carry to term, and give birth to healthy children in Martian gravity has never been tested, cannot be tested until people are actually living on Mars, or until we build rotating habitats that simulate partial gravity on Earth or in orbit, which we have not done. The developmental biology of a human embryo is exquisitely sensitive to mechanical forces. Gravity plays a documented role in cell division, in the formation of the inner ear, in the development of the cardiovascular and musculoskeletal systems. Research on rodent reproduction in space has shown that microgravity significantly affects reproductive biology. A 2021 study published in NPJ Microgravity demonstrated that mouse embryos could develop to the blastocyst stage in microgravity, which was encouraging, but the full developmental arc from conception to birth to healthy adult life in a partial gravity environment is something we have essentially no data on for any mammal, let alone a human being. A child conceived and born in Martian gravity would develop in a body shaped by that gravity. Their bones, their muscles, their cardiovascular system, their inner ear, all of it would form under conditions that no human skeleton or cardiovascular system has ever formed under before. Would they be healthy? Would they be able to function normally by Martian standards? Would they be able to visit Earth, even if they wanted to? We genuinely do not know. The possibility that the first generation of true Martians, people born and raised entirely under Martian gravity, might be physically incapable of surviving in Earth's gravitational environment is real, not science fiction. It is a biological extrapolation grounded in what we understand about developmental plasticity and gravitational adaptation, and it raises questions that are not just medical but deeply human. Questions about identity, about belonging, about what it means to be from a place you can never leave. The radiation picture for long-term habitation is equally sobering. We discussed in Part 6 the daily radiation dose on the Martian surface and the options for mitigation, underground habitats, regolith shielding, storm shelters for solar particle events. For a 2 to 3 year mission, these mitigations, imperfect as they are, represent a calculated and arguably acceptable risk. For a lifetime of habitation, they need to be not just acceptable but genuinely protective, and the cumulative radiation dose of a lifetime spent on Mars, even with the best available shielding, would almost certainly exceed what any human population on Earth experiences, and would significantly elevate lifetime cancer risk, potentially shorten lifespans, and create health management challenges that a Martian medical system would need to be equipped to handle across an entire population, not just a small crew. Genetic research into radiation resistance is one of the more speculative but genuinely interesting avenues being explored. The tardigrade, an extraordinary microscopic organism famous for its ability to survive in conditions lethal to virtually all other life, including the vacuum of space and intense radiation, produces a protein called DSUP, or damage suppressor, that physically shields DNA from radiation damage. Researchers have successfully expressed D in human cells in laboratory conditions, demonstrating that it reduces radiation-induced DNA damage by roughly 40%. This is preliminary research, nowhere near clinical application, but it represents a direction, a conceptual pathway toward biology-based radiation protection that over decades of development could contribute to making long-term Mars habitation more sustainable for the human body. Then there is the atmosphere. Because one of the most transformative and most controversial ideas in the entire conversation about Mars's long-term future is the possibility of terraforming the planet, changing its atmosphere, its temperature, its surface chemistry over geological timescales to make it more hospitable to life, ultimately, perhaps, making it breathable. The concept of terraforming Mars has been discussed seriously in scientific literature since at least the 1970s, when Carl Sagan himself wrote about the possibility in a 1973 paper in the journal Icarus. The basic idea is to trigger a runaway greenhouse effect on Mars, to release enough greenhouse gases into the atmosphere to warm the planet, which would cause the carbon dioxide locked in the polar ice caps to sublimate into the atmosphere, further warming the planet, which would release more carbon dioxide in a self-reinforcing cycle that could, over centuries or millennia, dramatically thicken the Martian atmosphere and raise surface temperatures to ranges less immediately lethal than the current -60 degrees Celsius average. Various mechanisms have been proposed for initiating this process, redirecting sunlight using orbital mirrors, manufacturing powerful greenhouse gases, perfluorocarbons, for instance, on Mars and releasing them into the atmosphere, importing ammonia-rich asteroids by nudging them into Mars-intersecting orbits. Each of these approaches has genuine scientific basis. Each also has staggering practical challenges in terms of the energy, the timescales, and the engineering required. A study published in Nature Astronomy in 2018 by Bruce Jakosky of the University of Colorado Boulder and Christopher Edwards of Northern Arizona University poured cold water on some of the more optimistic terraforming timelines by systematically analyzing the available volatile reservoirs on Mars, the carbon dioxide, water, and nitrogen that could theoretically be mobilized to thicken the atmosphere. Their conclusion was that even if every accessible source of carbon dioxide on Mars were released, from the polar ice caps, from the regolith, from subsurface deposits, the resulting atmospheric pressure would reach only about 1/20th of Earth's sea level pressure, enough to warm the planet meaningfully perhaps, but nowhere near enough to create a breathable atmosphere or allow liquid water to persist on the surface across most of the planet. This does not mean terraforming is impossible. It means it is harder and slower than the most optimistic proposals suggest, and that the carbon dioxide reservoir accessible by current proposed methods is insufficient on its own. Nitrogen, which makes up 78% of Earth's atmosphere and is essential for diluting oxygen to breathable concentrations, is dramatically scarce on Mars. Some nitrogen is locked in the regolith, but the quantities known to be accessible are a tiny fraction of what would be needed. Importing nitrogen from elsewhere in the solar system, Titan, for instance, which has a nitrogen-rich atmosphere, is a project of such staggering scale that it belongs more to the realm of civilizational ambition than near-term planning. What this means practically is that any human settlement on Mars for the foreseeable future, and foreseeable here means centuries, not decades, will be enclosed, pressurized, separated from the Martian environment by walls and seals and airlocks, not by a terraformed atmosphere breathable under an open sky. The dream of walking on Mars without a suit, of looking up at a blue sky, of feeling Martian rain, that dream, if it ever becomes reality, belongs to a timescale measured in centuries to millennia and requires technological capabilities we do not yet possess. What is achievable on a shorter timescale, decades rather than centuries, is something more modest but still extraordinary, a growing, increasingly self-sufficient settlement that produces its own food, its own air, its own water, its own energy, its own basic manufactured goods from Martian resources, a community that can sustain itself through the gap between supply missions from Earth and eventually through longer and longer periods of independence. A society in miniature, developing its own culture, its own governance, its own identity, shaped by the specific demands and beauties of the world it inhabits. Food production is one of the most tractable of these challenges, and also one of the most fundamentally human. The experiments with plant growth in space and Mars analog environments have been genuinely encouraging. The veggie facility aboard the International Space Station has successfully grown multiple varieties of lettuce, radishes, kale and other crops in microgravity using LED lighting and specially designed growth media. The Eden ISS project, a greenhouse facility operated in Antarctica as a Mars surface analog, has produced substantial quantities of fresh food, cucumbers, tomatoes, herbs, lettuce, in a controlled environment that mimics some of the constraints of a Mars habitat. Plants are extraordinarily adaptable. Given the right spectrum of artificial light, the right nutrient solution, the right temperature and humidity, both of which a Mars habitat would maintain carefully for the crew's own comfort. Many crop species can grow productively without natural soil or sunlight. Martian regolith itself, after treatment to remove perchlorates and other toxic compounds, could potentially serve as a growth medium supplemented with nutrients. Research groups have grown plants in simulated Martian soil analogues with some success, though the yields are lower than in optimized hydroponic systems, and the perchlorate removal step is non-trivial. Over time, as organic matter accumulates from plant growth and decomposition, and as microbial communities, carefully selected and managed, develop in the growth media, the agricultural productivity of a Mars settlement could increase substantially. The first colonists will be eating carefully managed hydroponic crops. Their grandchildren might be farming in something approaching genuine Martian soil, biologically amended over decades of human habitation. Energy is the other foundational resource. A Mars settlement needs power for life support, for food production, for manufacturing, for heating, for communication, for every system that keeps the habitat livable. Solar power on Mars is less effective than on Earth. Mars receives roughly 43% of the solar irradiance that Earth receives due to its greater distance from the Sun. Large dust storms can reduce that further for weeks or months at a time. Solar power is viable, especially for smaller installations and during favorable seasons, but a growing settlement with expanding energy needs will almost certainly require nuclear power. Small modular fission reactors, compact, robust, capable of operating continuously regardless of weather or season, are the most seriously discussed power source for large-scale Mars habitation. NASA's Kilopower project, which developed and tested a small fission reactor design specifically intended for space surface power applications, demonstrated a working reactor at the Nevada National Security Site in 2018, producing approximately 1 kilowatt of electrical power. Scaled-up versions in the 10 kilowatt range could power a small outpost. Further scaling could support a growing colony. The technology is viable. The engineering challenges of operating a fission reactor on Mars, managing heat rejection in the thin atmosphere, shielding the crew from reactor radiation, maintaining the system through years of operation, are substantial but not fundamentally different in kind from the challenges of operating fission reactors in remote terrestrial environments. Water is perhaps the least concerning of the foundational resources, which is itself remarkable when you consider that we are talking about a planet whose surface appears bone dry. Mars has water. Substantial quantities of it, locked as ice in the polar caps, buried as permafrost in the subsurface at mid-latitudes, potentially present in significant deposits, accessible to drilling at depths of a few meters in some locations. The SHARAD and MARSIS radar instruments aboard Mars orbiters have mapped extensive subsurface ice deposits. Confirmation of near-surface ice accessibility in specific candidate landing regions is one of the primary objectives of ongoing orbital reconnaissance. A settlement located within reach of accessible water ice has a resource that can be processed into drinking water, into oxygen for breathing, and into hydrogen and oxygen propellant, arguably the three most critical consumables of any Mars surface operation. Now, there is something profound that emerges when you look at all of these challenges together: the food production, the energy, the water, the radiation shielding, the atmospheric management, the medical care, the psychological support structures, and realize that really solving them at scale, requires not just engineering but something more like civilization building. It requires developing, in miniature and from scratch, all of the interlocking systems that human societies on Earth developed over thousands of years of trial and error and catastrophic failure and gradual refinement. The first Mars settlers will be building civilization under time pressure with limited resources in an environment that punishes every mistake immediately and severely. They will need to be simultaneously engineers and farmers and doctors and psychologists and politicians and philosophers. They will need governance structures, ways of making collective decisions, resolving conflicts, distributing resources fairly, managing the tension between individual freedom and collective survival that is the fundamental challenge of every human community ever formed. And they will be doing all of this in a place where there is no established precedent, no inherited wisdom, no cultural tradition developed specifically for this environment. They will have to invent it in real time. under pressure, in a way that is the most human thing about the entire enterprise, because that is what we have always done. Every civilization that has ever existed began as a small group of people in a difficult environment, using the tools and knowledge they had, improvising what they lacked, failing in ways that were sometimes catastrophic and sometimes merely instructive, and gradually building something that outlasted them. The settlers of Mars will be doing that on a cosmic stage, with the whole of Earth watching, with the accumulated scientific and technological knowledge of our civilization behind them, but with the same fundamental human challenge at the core of it all. How do you build something that lasts in a place that does not want you there, starting from almost nothing? The answer, as it has always been, is one day at a time. One problem solved, one failure learned from, one generation handing knowledge to the next, until the knowledge becomes culture, and the culture becomes identity, and the identity becomes home. Mars will become home. Perhaps not in our lifetimes. Perhaps not for several generations after us. But the first humans who land on that rust-colored world will have started something that, if our civilization survives long enough and remains curious enough and brave enough, will end with human beings who have never known any other sky looking up at the moons of Mars. Phobos rising in the west, setting in the east, completing its orbit in just 7 hours and 39 minutes, and feeling, in whatever way the word means to people who have never seen Earth, at home, and here, at the edge of that vision, 1 foot in the terror of what the first mission will demand, and 1 foot in the wonder of what it might ultimately become, is where I want to pause. Because we have covered an extraordinary amount of ground in this video. We have walked through the radiation of deep space, the dissolution of bone in weightlessness, the psychological grinding of isolation, the engineering nightmare of landing, the chemical hostility of the Martian surface, the political and human weight of loss, and the civilizational scale of what long-term presence on Mars would truly require. But there is one final dimension we have not yet addressed. One question that has been hovering at the edge of everything we have discussed, that connects all of it to something larger than any single mission or any single generation of explorers. A question about what Mars itself might tell us about life in the universe, and about what finding the answer, one way or the other, would mean for how human beings understand their place in the cosmos. There is a question that has followed human beings for as long as we have been capable of looking up at the night sky and wondering what looks back. Are we alone? It is the oldest scientific question that remains genuinely, completely unanswered, not partially answered, not answered with reasonable confidence pending confirmation, completely, utterly, profoundly unanswered. We have searched. We have listened with radio telescopes pointed at thousands of stars, scanning frequencies where a technologically advanced civilization might be broadcasting. We have analyzed the atmospheric signatures of exoplanets orbiting distant suns, looking for the chemical fingerprints of biology, oxygen, methane, water vapor in combinations that chemistry alone cannot easily produce. We have sent spacecraft to every corner of our solar system, photographing moons and probing atmospheres, and drilling into the surfaces of worlds that might, under the right conditions, harbor something alive. And so far, silence. Beautiful, humbling, slightly terrifying silence. But Mars is different. Mars is not a distant exoplanet whose atmosphere we can only study through the blurred light of a telescope. Mars is not a radio signal that may or may not contain meaning. Mars is a world we can reach, a world we have already sent machines to, a world whose rocks we are already drilling into and analyzing with instruments sophisticated enough to detect organic molecules at the parts per billion level. And Mars, unlike almost any other world in our solar system beyond Earth, has a history, a documented geological chemical history that strongly suggests it was once a place where life could have existed. Let us be precise about what that history tells us, because precision matters enormously here, and the line between what the evidence shows and what we would like it to show is one that science demands we respect absolutely. 4 billion years ago, Mars was a dramatically different world. We know this not from speculation but from the geological record preserved in its ancient southern highlands. Some of the oldest exposed terrain in the solar system dating back to a period called the Noachian, roughly 4.1 to 3.7 billion years ago. During the Noachian, Mars almost certainly had liquid water on its surface. The evidence is extensive and comes from multiple independent lines of inquiry. Valley networks carved by flowing water lace, the ancient highlands in patterns recognizable to any geologist who has studied river systems on Earth. Deltas, fan-shaped deposits of sediment formed where rivers enter standing bodies of water, are visible in orbital imagery at dozens of locations, including Jezero crater, where Perseverance is currently operating. Minerals that only form in the presence of liquid water, phyllosilicates, carbonates, sulfates, have been detected from orbit and confirmed on the surface by rovers. The chemical signature of an ancient, wetter Mars is written in its rocks, and it is unmistakable during this same period, the Noachian and the early Hesperian epoch that followed it. Mars also had a thicker atmosphere than it does today, generated in part by volcanic activity that has since largely ceased. It had, as we discussed earlier, a magnetic field that protected its surface from the worst of the solar wind and cosmic radiation. The surface pressure was likely high enough to allow liquid water to persist. The temperature, while cold on average, was probably punctuated by periods of relative warmth driven by volcanic activity, by impact heating, by the greenhouse effect of a thicker atmosphere. In other words, 4 billion years ago, Mars may have had the conditions necessary for life. And crucially, 4 billion years ago, life already existed on Earth. The oldest confirmed traces of life on our planet, microbial mats preserved in ancient Australian rocks called stromatolites, chemical signatures of biological activity in the oldest sedimentary formations we have found, date back roughly 3.5 to 3.7 billion years. Some researchers argue for evidence of life even earlier, approaching 4 billion years ago, which means that at the moment when Mars was at its most habitable, life was already present, already metabolizing, already leaving its chemical signature on the sister planet next door. Did life arise on Mars independently during that window? Did the same chemistry that sparked biology on Earth also ignite it on Mars? Given similar starting conditions, liquid water, organic molecules, energy sources, mineral surfaces, to catalyze reactions, or did life perhaps travel between the two worlds, carried on rocks blasted into space by asteroid impacts, a process called lithopanspermia that is physically plausible and has been seriously studied? Mars and Earth have been exchanging material throughout their history. We have found Martian meteorites on Earth, pieces of the Martian surface blasted into space by ancient impacts and eventually captured by Earth's gravity. Some of those meteorites have been shown to be capable of carrying microbial hitchhikers through the interplanetary journey under the right conditions. Could life have seeded Mars from Earth, or Earth from Mars, or both worlds from some common source? These are questions that the first human geologists to walk the surface of Mars will be positioned to answer in ways that robotic missions, for all their sophistication, fundamentally cannot, because finding life, or the preserved traces of ancient life, on Mars requires the kind of search that benefits enormously from human intelligence, human intuition, and human dexterity operating directly in the field. Consider what a trained geologist can do, standing in front of an outcrop of ancient rock that no robot has ever been able to do remotely. They can run their fingers along the layers, feeling the texture, the grain size, the subtle differences in hardness that speak to different depositional environments. They can recognize, in an instant, the visual pattern of a microbial mat preserved in ancient sediment, the distinctive wavy laminations, the specific coloration, the three-dimensional structure that a camera image flattened to 2 dimensions might render ambiguous. They can pick up a rock, turn it over, split it open along a natural fracture to expose a fresh surface that has not been touched by the Martian surface environment in 3 billion years, and examine what is inside with eyes and instruments simultaneously. They can make the kind of rapid, iterative, contextual decisions that distinguish a great field geologist from a merely competent one, the ability to read a landscape and know instinctively where the most interesting rocks are likely to be, to follow a geological story as it unfolds in the terrain. The Perseverance rover is a marvel of engineering. Its scientific payload is extraordinary, but it moves at a maximum speed of roughly 0.2 kilometers per hour on good terrain. It requires several days to plan, uplink, and execute a single complex sequence of scientific operations. A human geologist on the Martian surface could cover in an afternoon what Perseverance covers in months, and the search for biosignatures, for the chemical and structural traces that life leaves in rock, is the kind of search that benefits enormously from that speed, that contextual intelligence, that ability to recognize the unexpected and respond to it immediately. Now, here is the question that sits beneath all of this, the question that makes the search for life on Mars not just scientifically important, but philosophically transformative in a way that is difficult to fully articulate without sounding hyperbolic. Though the hyperbole, in this case, is entirely justified by the stakes. What would it mean if we found it? If the first human geologists on Mars, crouching over an ancient outcrop in the floor of Jezero crater or the walls of an exposed ancient riverbed, found unmistakable evidence of past microbial life, fossilized structures, isotopic signatures, complex organic molecules in patterns that biology produces and chemistry alone does not. What would that discovery mean for the universe as we understand it? It would mean that life is not a miracle. It would mean that life is not an accident so improbable that it happened only once in the 4 billion year history of a solar system, with 8 planets and dozens of moons and an asteroid belt and a vast cloud of comets. It would mean that the chemistry of life, the self-replicating, energy-harvesting, complexity-generating chemistry that produced everything from bacteria to blue whales to human beings capable of asking questions about their own origins, is something that the universe does when given the right conditions, something that happens, something that emerges from matter and energy and time with a regularity that, once life is found in 2 places in a single solar system, makes it almost inconceivable that it has not happened billions of times across the 2 trillion galaxies that fill the observable universe. The implications cascade outward from that single discovery in ways that touch every domain of human thought. Biology, obviously, the discovery of a second independent origin of life would transform our understanding of the mechanisms by which life arises, potentially revealing universal principles of biochemistry that we cannot currently see because we have only one example. Philosophy, the question of what it means to be alive, of what consciousness is, and whether it is unique to Earth, would be permanently, irreversibly altered. Religion and culture, the meaning-making frameworks by which billions of human beings understand their place in the cosmos, would face a challenge and an invitation simultaneously. The challenge of incorporating a universe teeming with life into worldviews developed for a universe in which life might be unique. The invitation to expand those frameworks to something even more extraordinary than they already contain. And if we do not find it, If the first human geologists search the most promising ancient sites on Mars and find no trace of biology, past or present, that absence is also profoundly informative. It suggests that even with liquid water, even with the right chemistry, even with billions of years of opportunity, life does not always arise. It narrows the probability estimates. It makes the universe feel, in some ways, a little more lonely. And it makes the life that does exist on Earth, that has existed here for nearly 4 billion years, that has survived 5 mass extinctions and produced the extraordinary diversity of forms we share this planet with, feel all the more precious, all the more worth protecting, all the more worth understanding. Either answer changes everything. That is the extraordinary position the first Mars crew will occupy. They will be not just explorers, but the people who finally, after centuries of wondering, deliver the answer to the oldest question our species has ever asked. Whatever they find in those rocks, life or its absence, they will bring back knowledge that reshapes the human story. And here is what moves me most deeply about all of this. When I sit with it long enough to feel its full weight, the atoms in the body of every person who will ever walk on Mars were forged in the nuclear furnaces of stars that lived and died billions of years before our sun existed. The iron in their blood was produced in the final moments of a massive star's life, scattered across the galaxy in a supernova explosion, eventually gathered by gravity into the cloud of gas and dust that collapsed to form our solar system 4.6 billion years ago. The carbon in their DNA, the oxygen they breathe, the calcium in the bones that will thin during the transit, all of it is stardust, literally, materially. The universe making something complicated and self-aware out of the wreckage of its own earlier generations of stars. Those first footsteps on Mars will be the cosmos touching itself. Stardust reaching across the void to land on stardust. Matter that began its existence in the heart of a dying star, that spent billions of years being shoveled through geological and biological processes on one small world, that organized itself into a creature capable of curiosity and courage and grief and wonder, that matter crossing the space between worlds and arriving finally on a surface made of the same ancient stellar debris. There is no frame large enough to hold that fully, no metaphor adequate to the reality of it. You can describe it scientifically, as I have tried to do throughout this video. You can describe it poetically, as Sagan and others have. You can describe it mathematically in the equations that govern orbital mechanics and nuclear physics and the folding of proteins. But in the end, what it is simply this: the universe, through us, going to see what else it made. And that, more than the terror, more than the danger, more than the bone loss and the radiation and the 7 minutes of terror and the perchlorates in the soil and the grief of being impossibly far from home, that is what the first Mars mission truly is. It is the universe becoming more aware of itself. The first human beings to reach Mars will carry every fear and every fragility we have talked about in this video. They will be vulnerable in ways that are humbling to contemplate. They will be risking everything, their health, their relationships, their lives, for something that cannot be guaranteed to succeed and cannot be made completely safe. They will cry, probably, when they land. They will feel things for which no language yet exists, because no human being has ever stood where they are standing and looked out at what they are looking at. And they will look up at some point during their time on that world and find a small, blue-white star in the Martian sky, brighter than anything else up there, but still just a point of light, still just a star among stars to an eye that did not know where to look. And they will know, with a completeness that no astronaut in low Earth orbit has ever quite felt, because Earth was always huge and close and overwhelming in their sky. They will know what that light is. They will know that everything they have ever loved, every person they have ever cared for, every landscape that has ever moved them, every piece of music that has ever broken their heart open, every meal shared with friends, every ordinary Tuesday afternoon that felt unremarkable at the time, but which memory has made luminous. All of it is there, in that point of light, 225 million kilometers away across the cold dark, and they will still choose to be where they are, because that is what it means to be human. To look at the impossible distance, to feel the full weight of what it costs, and to go anyway, to carry the fragility of biology into the indifference of the cosmos and insist, against all reasonable odds, on the value of the journey. The first humans to reach Mars will be terrified, they will be brave, they will be broken in some ways and made whole in others. They will suffer things we cannot fully anticipate and discover things we cannot fully imagine. They will be, in every sense that matters, the best of what our species is capable of when it decides that the horizon is worth crossing. We are made of the universe, and the universe, it turns out, is the kind of thing that looks at itself and wonders, that sends pieces of itself across the void to ask questions, that organizes stardust into creatures capable of awe, capable of grief, capable of choosing to go anyway. That is the terrifying, magnificent, heartbreaking, extraordinary fate of the first humans to reach Mars. And honestly, I would not have it any other way. If this video made your jaw drop, just wait until you see what daily life on Mars would actually look like at the video on the screen. We are talking toxic soil, crushing isolation, and a sky that will never, ever feel like home. Let's explore why Mars would be a horrible place to live. Trust me, you are not ready for it.